Kalimera from Cyprus. Good morning. Thank you all for coming to our second day of the workshop. Yesterday was more organic remains and case studies. Today we're going to focus on materials and data. The speakers today are monopolized by Promised. It's the Cyprus Institute, the University of Leuven, and the University of Cambridge, where while yesterday it was a more diverse crowd. We start today with Dr. Sorin Hermon, who is going to talk about advanced methods of in-situ artifact analysis based on integrated analytical and digital approaches. Sorin.
Thank you, Evie, for the introduction and the opportunity you gave me to speak at this workshop. I will start immediately with our approach in studying artifacts and why do we study them. What I will try to convince you that's important and interesting is to integrate digital technologies with analytical methods, with imaging, when we analyze in situ artifacts or in the lab. The location of the analysis is not really important, only the in situ requires and puts some more constraints. So when we analyze artifacts, we have in mind the chaîne opératoire concept, which basically looks at the materiality of an object, how it was done, how it was made, the technology involved, which the French came up with a very nice term, connaissance, which is the memory of knowledge of technology. Then techniques of production, which is the savoir-faire. It's the knowledge of an artisan on how to do things. Then the chaîne opératoire next stage is handling and use, how the object was manipulated, how it was handled, on which materials has been used, how, and so forth. And finally, how the object was discarded and which are the taphonomic processes that had an impact on the object and on the shape and structure of it as we see it today. So when we have in mind this kind of approach, we need to have a holistic approach, of course, to look at the object in its entirety. There are more and more constraints on using non-invasive and non-destructive methods, meaning that we should not touch the object or extract samples or use methods that in some way may harm the object under analysis. Of course, this very often limits the analysis, but we need to come up with new methods in order to answer these constraints. Then another important aspect is integration of measurements, meaning that if we have several methods that we apply, we should look into a method on how to put everything together, not only at a database level, but also sometimes on integrating the analysis themselves and the methods themselves. As much as possible, we should work on predefined protocols agreed upon a widest possible range of researchers, so we know that what we do can be repeated elsewhere in another environment and still we will get solid results. And finally, I'm sure all of you witnessed a big pressure from the European Commission, and not only, for open data and open science, meaning that we should be able to share our data, and the data that we share is of some value for others to reuse it. So from that perspective, I would like to briefly make a small break and talk about the FAIR data principles. I'm quite sure every one of you heard about them, but I just want to remind a bit. They talk about 4 main concepts. Each one of them has many other sub-concepts, but the FAIR data principle talk about findable, so data has to be finded somehow from the big amount of data that we have now in all kinds of formats and in all kinds of places. This data has to be accessible, meaning that we have access to it. of course, in digital, we were talking always here about digital data. The data has to be interoperable, meaning that if we use not only one operating system or another, we still should be able to open the data, but also to have the data in such a way that we can integrate it with another type of data, with another type of format. And of course, we should be able to reuse this data for either research, education, innovation, creative industries, and so forth. So in order to get to have some fair data in our scientific measurements and the derivated conclusions, interpretations, and so forth, one of the basic requirements is to have an explicit description of data provenance. That's the basic and most fundamental request from data in order to be able to assess its quality. Otherwise, we are left with an Excel file, an image, and we actually don't know what we can do with it. Then, and this is related, we should be able to assess the quality of the data in order to know what to do with it. What can we do with that data? We can use it for advanced research, for education only, maybe only to create a nice video game, or for a Hollywood movie. And finally, there is an ongoing, rightfully, request on have very clear intellectual property rights. And this is related not only to the reuse of data, but very often it deals also with ethical issues, particularly when we're dealing with bioarchaeology, community archaeology, and so forth. So when we are operating in the field, this is a very old project actually, but it was a pioneering project more than 10 years ago. Following actually some models that were operating in Europe already with the MOLAB. At the Cyprus Institute, we submitted an application for structural funds. And the idea was to create an updated and upgraded MOLAB by setting up not only a truck that would move instruments, but actually a working environment which is on wheels and can access many places, and would be able to perform integrated analysis, meaning that the instruments that we choose can talk to each other. So the concept of Star Lab was to have a mobile lab, so not a place to transport instruments like the MOLAB in Europe, but actually to have a working environment that we can bring it in the field, and with instrumentation that can have a nice dialogue one with the other and complement each other. So the basic components were geophysics, 3D documentation of both large-scale remains, sites, monuments, but also small-scale, which require a much higher resolution. Analytical methods, so mostly XRF and FTIR, and a wide range of imaging techniques from a variety of perspectives, hyperspectral, multispectral, reflectography, and so forth. So, believe it or not, well, I'm sure you believe it, but I hope you believe it, one of the main challenges in setting up such a lab are the logistics. How you dismantle, mantle, put back, and make operationable instruments that are really not supposed to move too much. So you see here that we had to customize boxes for everything. We had to be very creative on how we are using the instruments in all kinds of environments that really are not fitted to be a laboratory space. And this is one of the still, let's say, unresolved or partially resolved challenges when we are working in the field, because we're using very sensitive instruments in a sometimes very harsh environment. So coming back to that environment, as keeping in mind the FAIR data principles, a major effort, and this is also not easy to do when you're in the field, is to capture and document correctly the environmental conditions of the instruments that we're operating and all the calibration process that we do. So in order to assure that what we do, of course it's right, but it's also we can transmit this assurance to other people that will use the data later on. So I'm just giving here an example of how when we are dealing with data, we have to consider the entire process of data transformation from the data itself, the raw data, process data, post-process data, interpreted data, and finally the publication itself. And I brought here a quite simple diagram showing how we move from one step to the other using a wide range of instruments, what kind of methods we are using in order to post-process this data, and what are the implications of every step. So actually, you see now, I hope that when we are talking about open science and open data, actually we have to put out a lot of things before we say, okay, our data is good to go outside. How much of the raw data that we have should go outside? Okay, it's up to us to convince that this is the enough and necessary information that should go out. Also, it's very important to understand how all this data is related to our interpretation. So I put here some concepts of what do we do with the data that we have in order to be able later on to link between our conclusions and our method of acquiring data. Because this is another aspect of that relates to quality. How do we balance between our research question, the methodology that we used, and the data and the questions that we had up front? So this is a basic scheme for analytical measurements, and we have a similar scheme for the 3D data. I will just let you to look at that. Basically, you see here the steps that we are using when we are acquiring 3D data and then manipulate it for geometry analysis, shape analysis, pattern recognition, and so forth. Where at the end of this mind map, we have the same questions to be answered. So this is really where we are trying to merge the two domains. And I will give you some examples on how we do that. So as a case study, we are working our latest engagement with an archaeological site is Pila Kokkinokramos near Larnaca. It's a late Bronze Age site with a very unique history. Because it was very short-lived, quite intensively, there's a lot of material there, even though the architectonic remains are not so impressive, but the material culture is incredible. So because this material is so heterogeneous, because the site was very short-lived, it is very important, and it is in a very crucial, it is located in a very crucial time span for the history of Cyprus. Having an in-depth analysis of objects of the material culture, it's very important. So one of the first examples is this, I have this object here. It is I can use it is an alabaster flask, and up here you can see its archaeological context, which by itself is very interesting, because it was found, here you see the moment of founding, it was found in a niche dug in the bedrock, and the Canaan jar was covering it, was hiding it. So obviously it had some really important story to tell. once the object was uncovered and emptied, inside there were many, well, not many, but several other very interesting objects which are part of a discussion elsewhere. So the object underwent a typical treatment. It was taken out, cleaned, and a drawing was made. Passing by really accidentally on the corridor where the drawer was doing her work, we said, okay, why don't we do something else? Can we play a bit with this object? So, okay, of course. So we did a 3D, and you can see here some quite important variations in the shape of the object between the 3D and the drawing. So the drawing is kind of altering the overall shape, which is normal because the drawing is mostly experience and eye and some rough measurements, and the 3D is much more accurate. But this is not all. We have looked with a range of imaging methods, and you see them here. We applied visible induced luminescence, ultraviolet imaging, then we used the microscope, the digital microscope, XRF and FTIR in order to understand what's going on the surface of this object. So the visible induced luminescence found immediately traces of something that was fluorescing, which in many cases this is an indication of an Egyptian blue, which is a synthetic color that was invented many, many years ago. Nobody knew about that before. Actually, when we came to play with the object, the analysis of the object was done from the point of view of archaeologists. So we discovered the Egyptian blue in various places. We took also digital imaging, and you see here the traces of this pigment. And the XRF analysis returned a quite clear answer that indeed we are talking about Egyptian blue, which of course changes quite a lot how now the archaeologists are looking at this object. Another example, much more complex, also because it is really unique, and this is another characteristic of the site. We find many, many unique objects, is this very small figurine found in a quite unclear context because it was found in a modern trench dug by the British soldiers who are operating in the base near the site. So this is the object. It's made of stone with some interesting carvings. Once it was cleaned, again, the very traditional process was to clean the object very well and then make an impression on material like plastilina. So once we started to analyze it, we started to discover many, many other things which otherwise they wouldn't have been discovered. For example, we did a really intensive survey with a digital microscope on the surface of the object. And actually that was and I think using a digital microscope with a detachable lens, because you can do surveys on surfaces elsewhere, or in this case we put the object under the lenses, so in order to have a higher magnification, and we found out quite a few colors, as you can see here detailed. Some of them we think there are contaminations, but other ones are really colors that may have been there because the object was used on different material. So you see how we characterize every different pigment. Now, because this is also my interest, 3D, we also did a 3D documentation of the object with very high accuracy. And this is maybe the place to mention that nowadays 3D is something quite easy to do. Many people do it. They take with photogrammetry, for example, and they have a point cloud, and then they transform the point cloud. There are all kinds of software that give automatic solutions. But actually, if you want to use this kind of approach in science, in research, you have to be very careful what you do and how you acquire your data, particularly if you are using software that you don't really know what's going on inside the software and how the software transforms an image into a 3D model. Because you may have quite a lot of geometric alterations that you actually are not even aware that they exist. So my suggestion is when you're using a 3D, ask a professional how to do it, and then talk together and think together what is the resolution that you want to achieve. Resolution meaning, in this sense, how much geometric information you want to put on a small square, more or less like, let's say, pixels in an image. So this is the object. This is the 3D snapshots from the various parts of the object. And one of the first things we did was to understand, to try to understand the history of this object. Because also when we were looking at it, it was clear that the marks overlap each other. They cut each other. So you see here, I mean, on the upper part is the object, how it looks today. And then when you see here, for example, this hole that cuts a line, or these marks that cut the line. So we separated it in order to see how the object may have looked in the various stages of its existence. The next step that we did was a bit more in-depth. And we said, okay, let's try to see if we can characterize these signs in terms of the manufacture itself. So there are three types of lines, lines, which we proposed that they were made with a chisel. Then there are crescent shape signs, which probably were made with a scalpel. By the way, if you have another suggestion for this term, please tell me, because my imagination stopped at the crescent shape. And then there are holes of various sizes, which are drilled in various places on the surface of this object. So when we were looking and separating between the different signs, it came out that the lines themselves are mostly made from two different parts. And we were able to say that with kind of certainty because of the shape of the lines themselves. So they go like that. And we could see also the marks, the lines, and the direction of the marks. So we proposed that in the case of the lines, the object was holed in a vise type, and these are the blows with the chisels from mainly two directions. When we look at the other signs, the crescent shapes, for example, it's a totally different approach. So you see here that they were made from many, many different directions. Probably the artisan was holding the object in the hand and making the sign, rotating it, again making, and again rotating it. So totally different approach, maybe two different artisans in two different episodes. The 3D allows also a lot of other things to do. So we can play quite a lot with scientific visualization. We can change renderings. We can change light projection. We can do very accurate measurements on the 3D. And you see here, for example, up here, it's a kind of internal, it's the negative, it's the reflection of the sign. So it's kind of a look from inside the object, how these carvings look like. Actually, they're negative. And you see how one sign cuts the other in a very clear way. Other nice things that came out, it's, for example, with the holes. You remember that the object was drilled. And we can say quite certainly that the object was drilled from two different directions, but in a quite perpendicular, parallel way. So the work done was of a high quality. Then we can look and analyze every hole, and I brought here an example of various stages of finishing of these marks. Some of them are really, really symmetric, other ones much less. Next to the site, next to the area where this object was found, in one of the areas in this room, a range of chisels were found, which are quite small, and maybe some of them were used for the manufacture of this, for the carving of this object. Now, and this is something quite nice that we can do again also with the 3D, we peeled the surface of the object, virtually of course, made a negative in order to show the impression of this object. So this is the virtual impression, but actually it's much more accurate than the real one on the plastilina. Also, it allows you to measure everything. So you see here the simulation of the movements of the object and the impact it leads on a surface. Then we do, 3D allows to do much more than that, and here is a replica that we printed in order to show also how we can, so we can play with the object, hold it, see what's the natural, let's say the natural gestures that you apply when you are holding it and you are trying to use it. And thinking in terms of use, we also found here, for example, some marks which may be remains of a rope that was around the object. Other interpretations are I put up here. In this case, you see there are a lot of signs, a lot of lines of different depth and apparently going nowhere because we couldn't really extract a pattern. And because I'm a prehistorian, this is kind of a recurrent thing in many cases where you have a stone that was used as a sharper. So this is for, these kind of signs are often used to sharpen tools. So to sum up, the what, how, and why questions of the workshop. In one object, we have many, many opportunities and possibilities to do a wide range of analysis, and we need to somehow combine them, and we need to somehow integrate them. So we suggest that one of the types of integration could be done on a semantic level. So once we set up a repository, we put the data in, and we need to describe somehow that data, we can use CDOC-CRM ontology. CDOC-CRM is the ontology in cultural heritage. It's an ISO standard. Not the only ontology, but it's one that received recognition as an international standard. And here is a diagram showing how we can integrate and express semantically the integration between analytical data and digital data. And I put down there an article that describes more in detail this approach. Another concept that we are proposing is to use 3D as a kind of glue for all the information and have the 3D upfront as a visualization tool, actually, on which you can locate, because 3D has X, Y, Z of every point, where you can locate images, where you can kind of geolocate images, data, and so forth. So, thank you very much.
Thank you, Sorin. So we're ready for questions here from the audience or online. Yes.
Yes, hello. Hello. I'm a conservator, so I don't like people touching the objects that I have cleaned. How would you see the method of 3D scanning objects and then having people studying them through the 3D scan instead of actually handling the objects with the detrimental effect of polluting them or damaging them or all these unwanted, unnecessary effects?
Yeah. Thank you for your question. This is right to the point, because on one hand, we have also noticed, especially when we're looking with a digital microscope and on imaging methods, a lot of contamination. So this is exactly what you're mentioning. The 3D has to be done in a very accurate way in order to be sure that what we hold and we manipulate, and actually 3D allows a lot of manipulations, but this kind of manipulation of an object should be done on a 3D that is as much as possible close to the original object. This is why there were also many European initiatives setting up large 3D data repositories, exactly to answer this question. Not only that, because once you have a 3D object and giving the proper IP clearances, you can reuse it in all kinds of different domains. For example, in conservation, it's extremely useful when you have a 3D of a fragmented object and you try to think what was the shape of the missing parts. So the 3D is the right solution because it gives you a geometric approach to the reconstruction. So I'm all in favor of scanning, having like mass digitization of objects and have their 3D there in order to be able to use them and not touch the originals. But the 3D has to be done in a controlled environment, in a controlled way, so we are sure that its geometry fits with the original.
Thank you, Sorin, for the talk. More a classical question. What type of stone is it? Do you know where it's from and what its function may have been?
So there were no work done yet on the type of stone. It's a green stone. I mean, you could see that as well, but this is a very generic answer. Still, analyses have to be done. In terms of use, we suggested several use. For example, because of this range of pigments that we found, it may have been used as marks on textiles, for example, decorations on textiles. On the other hand, we have these marks up, which I really don't know what they look like cuts, really like cuts. So it may be for sharpening, as I mentioned. We also try to look at the signs if there are some kind of symbols. And this is the period of the Cypromenon. But it's very far. I mean, you need a lot of imagination in order to come up with the letters there.
But in the context of Pila having so many imported artifacts, it could be from abroad as well as locally made. Question.
Yes. Yes, and the problem is that there is no analogy. Neither the shape, neither the signs, the stone maybe, but we really did not find in the archaeological record of the region and the broader region anything similar to that.
Any more questions? Sorry, something different from that, I think, but it's very relevant because it's about big data and stuff. Matthew Collins yesterday mentioned, and he was very happy, that Denmark is part of IRIS now. Can you tell us a little bit more about IRIS, since you're the expert on that?
Locally.
Locally, yes, locally.
Okay, IRIS is a European initiative, European research infrastructure on heritage science, meaning that its mission is to set up a European but also a worldwide infrastructure, not a network, meaning that it's not a network of labs, but it's actually an integrated platform where laboratories work together in order to achieve results in the field of heritage science. Actually, we also worked quite a lot to define what is the field of heritage science, and there is now a definition. IRIS is funded under the ESFRI initiative, so it's one of the strategic infrastructures in Europe. There are others in life sciences, in earth sciences, in humanities, in linguistics, and so forth. IRIS has currently 3 functioning platforms and 1 under development. So the 3 functioning platforms are FixLab, which is a network of large-scale laboratories, like synchrotron, accelerators, and so forth, fixed. And then there is MOLAB, mobile laboratories. There is one in France, there is one in Greece, we have one here, there is in Romania, in Poland, and so forth, and they move around to provide diagnostic services on the spot. Then there is ArchLab, which is the archives lab. So these are archives all over with scientific data, and they open them for investigation. And currently under development, because this is something very new, is DigiLab, the digital infrastructure of the entire platform, which I'm part of this development. DigiLab is supposed to gather all the information, all the data from FixLab, MOLAB, and ArchLab, and set up not only a data repository, but also virtual research environments. You have tools that will allow you to integrate with this data, and of course, connect DigiLab with EOSC, the European Open Science Cloud. IRIS provides also training, networking activities. There are if you have requests to go and work on a lab, you can do that. Labs, yes. IRIS was recently awarded another preparatory phase called Hyperion HS, which we have some colleagues here that also participate. That will help further on to develop IRIS.
Okay. Thank you very much. That was
we have, Evie, we have one question from online from Bart Cornelis. The question is, do you have suggestions for shiny objects that reflect light? Does the 3D scan still work?
Okay, thank you for the question. Of course, it depends on how much the objects are shiny. If they are very shiny, in that case, for example, we 3D scanned glass, and in order to scan that, we used photogrammetry, but high accuracy photogrammetry, using polarized lights. So we put polarized filters on the light sources, and we were moving them until there was no more reflection, and then we took the image. If we want to use optical scanners, which also are based on lights, we have to make sure that when we position the objects, they don't have shade.
Okay, no more questions. Thank you very much, Sorin, for this. Thank you. Hannah, you have to take it. We have 5 minutes, or rather like 7 minutes for the next talk, so I'll see you in 7 minutes. Here we are again, and I'm very, very pleased that I'm going to welcome Dr. Maria Dikomitou at the Cyprus Institute, who is going to talk about the interdisciplinary study of archaeological ceramics, a discussion about sampling and methods of analysis. Welcome, Maria.
Good morning and kalimera to all, both online and in person. I'm really happy to, Evie, and thank you very much for the invitation to be here with you today and talk about pottery analysis in archaeology. And I will start right away with answering the question, why ceramics? A basic question, but I think it's an important stage in order to follow the line of thought that I would like to guide you through today. So pottery is one artifact category that is recovered in abundance in every excavation. And not only in excavations, but in the field. We walk in the fields and suddenly the first type of material that we find in front of us is potsherds. It's the one craft that for several millennia consistently evolved both technologically and typologically and thereby tracks social evolution. It's not only objects that we are studying. Behind the objects is the people that actually produced them, used them, and finally discarded them. The importance of pottery also lies in the fact that it's a source of archaeological information, especially in the study of non-literate societies. And what I mean with that, and I will use a quote by Dean Arnold from his 1993 book. In his introduction, he wrote, "Ceramic artifacts are thus the products of the actual behavior of ancient people, and inferences of the past based on pottery can extend understanding of ancient societies beyond the verbal accounts of the learned, the wealthy, the privileged, and the influential." Basically, what we do, we study everyday people through ceramics. Beyond those that were inhabiting palaces and urban cities, through the modest medium, sometimes, of pottery, we can actually approach the everyday person that was living in the rural communities and understand better their everyday lives. Not all cultures have left to us sources of information regarding the production and the technology of production of pottery. The Egyptians, the Romans, the classical world have left enough material and enough sources. And actually, there are cultures where we can find the production logi, the tools and the debris, so that we can understand just a bit better how ceramics were produced. But there are those cases, and in Cyprus, this is more often than not the phenomenon, where our only source of information, our only evidence comes from the ceramics themselves. And this is why we need to find a strategy, a research design that can assist us to decode the information related both to their production, to their distribution, and their use from the potsherds themselves. What is pottery? Or what is clay? Depending from who is asking the question, the answer could be anything, tackling with issues of depositional context, of chemical composition, of mineralogical structure, of granulometry, meaning the size particles of the grains. For the archaeologists, though, and indeed the potters themselves that use the pottery, clay is that earthy, fine-grained material that, when combined with water, can become plastic and workable. And clays actually used in the production of archaeological ceramics are almost never pure from a mineralogical or a granulometric, meaning their particle size sense. Oops. They may consist of a mixture of clay minerals, fine and coarse components, and deriving from different sources through the decomposition and the weathering of rocks and a range of minerals. From the moment that the humankind discovered this unique materials properties and their manipulation, we can say that there was a technological milestone, because it assists them in every aspect of everyday life. And indeed, if we think that ceramics are basically water and clay with the assistance of fire and air, we can actually say that it was the first synthetic material that was produced by humankind. So here is our milestone. There are a number of properties that make clay and then the ceramic extremely useful to our everyday lives. First of all, they are inexpensive, they are found in nature, and they are easily accessible. When they are moistened, they become plastic and they can be shaped in different forms. They have high melting points, which means that they can be resistant to high temperatures, and they are long-lasting and hard-wearing, meaning that they can be transferred, they can hold weight, and another characteristic is that their thermal conductivity, meaning that they can be used in order to heat things and or process food. And also, they are inert to other substances, meaning that they can stay inactive, and that's why they can be used as containers in order to store substances or to transport them. Of course, not all clays have the same properties, and there are different ways to manipulate clays in order to achieve the properties that the potter has targeted. Therefore, different clays are used for the production of different artifacts. And cooking pots, for example, have the clays used for cooking pots have different properties from tableware, or pipes and tiles and bricks need different properties than, for example, tuyers used for channeling air in metallurgical activities. Therefore, we need to see the artifact, the final end product, in terms of both the initial raw material properties, but also the different stages that the potter has followed in order to come to the end product and the final properties that served its function. Artifact structure and composition, therefore, is a result of raw material selection and processing. Material properties mark the end product's performance characteristics. And the entire life cycle of an artifact is actually a series of interlinked and very closely associated technological and cultural choices. The potter, from the moment that he decides to create an artifact, he needs to think its function, how it can be durable and long-lasting, and how it can make it easily and produce it within the cultural context in which he belongs. Aesthetics are also really important to that end. So basically what we do is we reconstruct the different stages and we identify and document those technological and cultural choices of the potter towards during the production process. Most of the times we are not able to complete the entire puzzle and produce a clear and complete picture of pottery production. But even fragmented information, like fragments of the puzzle, are important in enhancing our knowledge of ceramic technology, how things were done, the know-how behind them, and the social and the cultural context in which they belong. I like to consider pottery that is not a soulless object. They are artifacts made by people, and each of these artifacts has a biography, has a life cycle that starts from the moment that the potter decided to produce the ceramic and continues until it was discarded. And even then, it's not over, because when we have it in our hands and we are studying it, we are interacting with it, and we give it we are giving a new meaning in their lives. All the different stages in this, all these different chapters in the biography of pots are called in the literature the chaîne opératoire, which is the operational sequence, that different stages from the beginning until the very end, that it involves not only the production but also the distribution, the movement, the circulation of pottery, but also its use and its reuse and its discard. The chaîne opératoire approach brings forward the notion of ceramic technology, which encompasses not only the end products, what we see in front of us, but also the materials, the actions, the cognition, the know-how that brings all these different elements together and making the pots live again in our hands. That's why gradually, through the decades and through scientific development, ceramics stopped being collectible objects, art objects, and became challenging archaeological artifacts, which we can decode, we can interpret, and from which we can extract information about past people. There is a multitude of questions that an analytical study of ceramics can cover, from function, contents, and absolute dating to production, distribution, and use. And there are all kinds of infrastructures and instruments with which we can actually achieve that. Production entails the technology of their manufacture. This means that the material study, whether this is chemical, mineral, or isotopic, essentially attempts to reconstruct the various steps of the operational sequence that we have talked about, followed by the potter, the craftsperson, throughout the production sequence, in order to define, identify, and record materials, techniques, and know-how involved in the manufacture of the ceramics under study, all based on investigations of their ceramic structures and compositions. So basically, we want to characterize the material. We want to get to know the material and document the different characteristics, its different attributes, in order to see how all of these fit in our broader picture. Why? Beyond production, beyond understanding ceramic technology, there are many, many different issues related to the production, including the mode of its mode of organization, is how standardized it is, how specialized it is, and how it can be compared to past technologies and later technologies in order to track technological evolution, but also social evolution. A certain mode of organization of production says things about the economy of the community, says things about how the society, the community is organized. And it also says things about the interaction between different communities as material is exchanged. So pinpointing provenance as a next step and defining local versus imported ceramics can actually assist us in understanding the scale of their distribution. Are they made only for local use? Are they made to be exported outside? And what are the characteristics of those locally produced and those exported? Are they the same or do they differ? How standardized they are? And all this information can give us an extra glimpse into exchange, into trade patterns, and finally into different modes of social interaction between people, between communities, between different regions. Determining provenance and technology, as I said, means material characterization, getting to know your material. This can be done with different ways. It can be chemical, mineralogical, isotopic, microstructural, mechanical, etc. Depending on your questions, the specific questions that the archaeology is asking and the material scientist is asking, the nature of the material, but also sampling. Can we actually sample and extract? Can we the only way is only to analyze non-destructively? What's our time frame? What is our budget? Money is so important. So all of these, in a way, define and put constraints or provide potentials for a specific kind of material characterization. And I give you here a fancy list of many and differing methods, both mineralogical and chemical. All of these different methods have similar goals and theoretical assumptions that we will talk about a bit later, and they are therefore largely complementary if there is the possibility, if there is the potential to use them in unison, they can actually broaden and open a new window for the questions that we are asking in terms of production, in terms of distribution, in terms of provenance. These methods are normally used to detect and document archaeologically meaningful compositional patterning groupings within ancient ceramic assemblages. And their data are in the forms of either mineralogical nominal information that can be descriptive, used and documented in words, or it can be values and measurements and long tables of numbers. All of these, however, as I said, have a similar background, and that is the provenance postulate, according to which the compositional differences within a single raw material source should be less than differences among two or more sources. Therefore, if an artifact is removed from the area from where it was produced, it still sustains some of the characteristics of the area from where it originated. And the final archaeological artifact, as I said, to some extent has exactly has similar chemical characteristics with the raw material source. And what we are trying actually is to trace the fingerprinting. So in order to associate the final end product with an area, with a geological region. Pinpointing provenance is certainly not a straightforward process and cannot be done without prior knowledge of the sites or regions surrounding geology. Most of the time it's good to have, in addition to the actual archaeological material, information for the assessment of the local geology. And if local sands and clays can be collected in order to be comparatively studied with our archaeological material, this makes the study even better and even more reliable. Of course, there are online databases now. There are so many publications for comparative studies that I mean, the sky is, in many cases, the sky is the limit in order to associate different products and different regions. And within, of course, networks of interaction, networks of exchange, and networks of trade. And with that, I would like to make sure that we always consider within a study both the natural and the cultural landscape. We must never forget that the ceramics do not stand alone. They belong both to a cultural landscape, or in a culture where they evolve, they produce, and they are used, but also they are they are associated also with the natural environment, as that and the materials that are accessible, and the natural landscape and how it's formed also affects both the production but also the distribution of pottery. Before saying a few more things about the various analytical methods, I would like to talk just a bit about mapping a research strategy. We often evidence projects that they just promise all these things at the beginning, and then at the end, what comes out is much more modest result. And I think it's very, very important from the beginning to set specific research goals, having acquainted your material. Not all material can answer all questions, of course. And as I said before, both the nature of the material and our sampling capability are important in forming our research questions. Asking realistic questions is important, considering the advantage and the limitations both of the material but also of the methods of analysis. Unfortunately, we don't have access to all types of different methods, and our local infrastructure sometimes are permitting only a certain analytical methodology. However, if we're realistic, we can actually ask a specific number of questions that we can actually answer. And by that is we select the best possible analytical means according both to our time and to our resources. And as I said, being realistic is what keeps you from being, what makes you systematic and what makes you able to answer the questions that promise things and not deliver afterwards. It's very, very important that any decisions we made and any methods that we select are all archaeologically informed and material specific. I think that a very important stage in the designing of a project is to know your material from a morphological, from a microscopic, from an archaeological point of view. In that way, your sample will be representative. You don't want, I mean, at the end of the day, you are analyzing a very small number of samples, and you want to talk about the entire population. So what you need to do is that you want to ensure that your sample can actually be, and the inferences that you made about your sample can be actually transferred to your population. This is not easily done. I mean, there are many times a lot of sampling biases that every one of us is doing. But I think that a thorough macroscopic study, a well-documented morphological study of the material when it's possible is important, and it makes you being able, it allows you to collect a representative sample so that you know exactly what you're sampling and what your sample represents. So that's why it is crucial to record and comprehend both quantitative and qualitative the ceramic assemblage under study. And as I said, archaeological inferences should be transferred from the sample to the ceramic population. This is where every project's value lies, that we can actually talk about the entire assemblage at the end of the day and not only about 20, 30, or 100 samples. Ceramic petrography is one of the most broadly used methods. It's not as expensive as other methods of chemical analysis. It's easily accessible. What you need basically is the infrastructure to prepare your thin sections and an optical polarizing microscope to study them. If you're lucky enough, you have also your camera and your scales in order to document them as accurately as possible. Ceramic petrography in the form of thin section is basically the study of very thin sections of the cross-section of the ceramic. The width is only 30 microns. For those of you that would like to understand the measurement unit, is basically the little first line in the ruler, that's the 1 millimeter. The 30 microns is actually 0.3 of that little distance. And it's very, very thin. It's almost transparent, not almost transparent. And it can be studied. This very thin section is fixed into a glass slide, and it can be studied under the optical polarizing microscope using both plane polarized lights and cross-polarized light, meaning that the light is directed in two specific directions, playing with the optical effects of the minerals, of the rocks, in order to identify them. And this is how it works. So basically, by looking at thin section under the optical microscope, you can talk about the types, the different types of mineral grains, of rock fragments, of the pores, the cracks, the fossils, all the different constituents that make up the fabric that you're studying. And the fabric refers both to the types, the different material that is found and recorded, but also to their arrangement, how they are found, their organization through the thin section, and their density and their shape, angular, spherical. All these have information embedded in them that can assist us in understanding the technology of the production of the specific fabric. And as we said, the end fabrics normally have similarities with the actual raw materials. Therefore, different fabrics can be associated with good knowledge of the geology of the region that we are studying, with with different regions. And in this case, for example, I give you some examples, a very igneous fabric full of gabbro fragments, which can be associated with the ophiolite, with the Trodos ophiolite, and it's very, very common in the central of the island. Or this very rich in mudstone fragments fabric, which is and in chert fragments, which is associated with the Paphos regions to the southwest of the island, or a very fine-grained micritic clay, which is very broadly used in sites on the north coast. So what we can do with good knowledge of the geology of the region, with sampling the geological environment, when we are lucky enough, we can associate our ceramic fabrics with a region and with a geological terrain, with a geological region. In addition to the compositional characterization of our fabrics and their association with specific geology, the ceramic thin section analysis has the extra advantage of providing information about technology, meaning that we can see information in a thin section about the processing of the raw materials of the clay that was used for the production of specific fabrics. In this case, for example, we see these. Okay, I lost it. In the upper slide, we see these red clay striations which can be used as evidence for clay mixing, or further down we can see two different fabrics. One of them is very refined. It has no large size inclusions, coarse fraction inclusions included in them in relation to the one it's in its right, where these large micritic limestone fragments suggest that there was not much refinement of the initial fabric. Or in this picture, photomicrograph at your left, you can see that the initial fine-grade material was tempered with some sort of sand. So we get all different kind of information regarding clay mixing and refinement, whether the material was the material was tempered, that means artificially there was artificial additions of another sort of material, whether this is an organic or organic. The information that we extract from the study of thin section can be very descriptive in nature, and we note them down in the form of nominal data. We describe them. We basically describe what we see using different visual charts and different reference information as our guides. There are two very important publications that we use. The one is by Ian Whitbread, and it's very valuable for the petrographers, appendix number 3 in his book on Greek transport amphorae, which was published in 1995. And then the other one is by Patrick Quinn, and it's a recent one, published in 2013. Both of them, in a way, they describe the ways in which we can describe our thin sections in order to aim towards a more systematic way that can be comparable between different researchers. This is not always the case. I mean, there are so many different ways in order to describe a thin section. You can be extremely analytical and very thorough and very focused to detail, or you can just give basic characteristics. However, if we try, I mean, at least in the Mediterranean, we use these two books as our reference guides in order to be as systematic as possible. Now, I make a parenthesis here. A USB microscope cannot be at any level compared to thin section, to the use of thin sections and the use of optical polarizing microscopes. But, and this is addressed to students and to people that do not have access to actual analytical equipment, the USB microscope that can be purchased online and can be found quite cheaply can actually give you images of the thin section, especially if this is quite polished and you see this doesn't work for some reason. I'm sorry. So, as you see, these two pictures come from the study of this thin section. And you can see that you can have some details of what the inclusions are. So an attempt is now being made that while we record our material macroscopically, we also take pictures using a relatively cheap USB microscope of the sections. Therefore, those that actually have access to a polarizing microscope and to thin sections at the end of the day, they can provide a more complementary, more well-documented picture of their fabrics. And those that don't can go then and compare their materials. So for comparative purposes, for those that actually have access to thin sections and to those that do not, it's good to use a USB microscope just to document your material in a way and have some sort of a platform to compare it to other published material. Now, ceramic petrography is not a panacea. Nothing is a panacea. It has its advantages, but also it has its limitations. And it's it's not always the appropriate method when your fabric is very fine-grained, or if your inclusions are omnipresent, like quartz and shell that can be found anywhere. In those cases, the ceramic petrography, like in these two slides below, you can see that it's not very useful. So in that case, you need to find an alternative solution. That's why I said it's important to know your material, because not all methods are appropriate for all kinds of materials. And this also applies to when you have very specific questions. And for example, I give you these two samples. They are made, for me, it's the same fabric. It's this igneous fabric full of gabbro fragments and the rock's constituent minerals that is found in the central of Cyprus around Rhodos. And when it's found in different areas, in different signs, and when it's found when you find different shapes from different periods being made from the specific fabric, you start wondering whether what you see is internal fabric variability within a specific raw material resource. Is it different raw material resources with similar mineralogical characteristics? And it makes you wonder how to approach it differently. And here is where a chemical method of analysis comes in, where it gives you additional information, and it can perhaps pinpoint differences, chemical differences in the material that you cannot see mineralogically. So, as I said, there are different, all these different methods are not always appropriate, and you need to know your material and you need to know your questions so that you select the most appropriate method. Now, I give you here two tables, data tables. First one, the upper one, contains information coming from neutron activation analysis, and the one below from portable XRF. These are two methods at different ends, and very reliable method, and you can see the large range, the elemental range that it provides, and then PXRF, the smaller number of elements measured. in both methods, and I put it on purpose. You can see the different archaeological information included, and I will explain now how important it is, especially in the case of the portable XRF. So even the different chemical methods give you different information, and very simple and straightforward indication is this one between the neutron activation and the portable XRF. It's this difference lies in many different reasons, and most straightforward one is the fact that the first one, the material is drilled. You can actually clean the body, the ceramic body, so that you know exactly what you have drilled and you have included in the sample. Whereas in the portable XRF, you just it's a non-destructive method. You just point your gun on the material, and in many cases, and I will show you next an example, you don't have even the option of actually choosing between analyzing the ceramic body and the slipped area of the vessel. There is also issues of geometry, because a lot of the material is spherical, so you cannot actually attach the gun and put it flat on the surface, and issues of cleaning the area and so forth. So each method comes with a number of parameters that you need to have in mind before choosing it. And also another important issue is the issue of comparative studies. Normally, laboratories that use neutron activation have developed calibration procedures so that their data sets can be comparable between them. In the case of portable XRF, in the case of my own study, for example, and I'm coming to it, this is not always the case. You can use it for a qualitative purposes, but you cannot always compare your data with those of others. Of course, even in the case of PXRF, and I need to be honest with that, there are now different procedures and different protocols developed by different researchers and different labs that start making it more, making comparisons more feasible. So in my own research, in recent years, I used portable XRF analysis in the study of early Bronze Age and Middle Bronze Age ceramics from Lapithos. We were very lucky that the material was stored in the Cyprus Museum in Nicosia. It was stored there for almost 100 years, and then Jennifer Webb from La Trobe University decided that it was time to document the material. And we were extremely lucky because she's one of those ceramicists that documents the material in the most thorough and well-documented way. And it was so important for us to use the information that she gave us regarding the morphology of the pots, their dating, their decorative attributes, their ceramic attributes, their fabric attributes as she was seeing them with the naked eye or with a simple lens, and introduced it in our data set in order to see whether there were any patterns. In most cases, and you can see here, we were analyzing entire vessels, and we could not, of course, distract them or destroy them just to pick a sample. So portable XRF was the appropriate method, first of all, because we were dealing with whole vessels, because the material was hundreds and hundreds of pots that we could not, of course, sample everything, and we wanted a thorough, large-scale analysis of the material in order to understand patterns of technological patterns and within the assemblage. So portable XRF was both cheap and fast in order to achieve that. And as you can see here, in most cases, we were analyzing the slipped areas, and you can see, and I put in on purpose this surface and crusted sometimes areas. We were trying to choose clean areas, but it wasn't always the case. And in more rare occasions, we were able to analyze both the ceramic fabric where the slip was chipped off, and the slips in order to distinguish between slips and bodies. So we used multivariate methods of analysis, that is principal components analysis and hierarchical clustering using R, using SPSS. There is another package called R that is used for multivariate statistics and for processing your data. And we were trying to see compositional groupings and patterns, and that could have some association with morphological groups, with wares and subwares, and how Jenny was manipulating the assemblage and whether there was correspondence between the analytical study and the morphological study. Our interpretation was based on group observation, so we were looking how groups of samples rather than individual samples behaved. And also data often included, and we had in mind that the data often included specific elements and not the entire elemental range, like in the case, for example, of neutron activation. So we were looking just a fraction of the compositional variability, and that's why it was important to see how groups of samples were repeatedly behaving in order to lead us to different arguments. And you can see here, while we were playing with the data, that we were able to, at least compositionally, to distinguish earlier subwares within a broader ware, and we could see how fabrics were evolved through time, and also how material that was morphologically distinguished as being important to the site was behaving in relation to material that we thought, at least morphologically, that they were locally produced. And I give you an example here with the black slip and red slip wares, and it doesn't show, okay, there is something. So all of the material here, this is what we thought that it was imported, morphologically at least, and indeed it differentiates itself from the bulk of the material that morphologically we thought that it was produced in Lapithos. It's also important to, when feasible, to combine techniques. This is for two main reasons. Firstly, you test the correspondence between your results, and you are feeling more confident of what you are producing. And then you're complementing analytical information with information that derive. I have to finish.
You have finished 15 minutes ago.
Really? Okay. Oh my God.
It's okay. It's all right. It's okay.
Okay, I will move. Oh my God. Okay, I will move forward. Oh my God, I'm so sorry. Okay, so in terms of correspondence between results, it is important to, I think the next one is better, to check correspondence between the results and correspondence between different analytical methods. As you can see here, the samples here were they were described, were labeled according to the to fabrics, and then they were clustered based to their chemical characteristics. And you can see here some good correspondence between the results, and you know that you can trust your data set. Okay, I will finish just with one word about scanning electron microscope and how important this instrument is, both for taking good quality digital images, but also for the elemental analysis, and when there are calibration potentials, both for quantitative but also for qualitative purposes. And just show you here the technique is used in order to understand your material. And here I show you pictures of microfossils and how well preserved they are. Or here the structure of clay particles, and in that case they are flaky nature, and in the right hand side how vitrified they are. I would like to finish, I really apologize for this, but just by saying that there are all sorts of methods out there for the analysis of ceramics. Not everything is appropriate. There must be a very good communication between the archaeologists and the scientists in order to develop a straightforward and a very efficient sampling strategy and a project strategy. And I apologize again, and I thank you for your attention. I'm so sorry.
Don't worry, Maria, it happens. When we're enthusiastic about the material, it happens. But unfortunately, we're not taking questions because we have to move to our next speaker, who is Professor Thilo Rehren, the director of Starcy. And we're very, very happy to have him here in Cyprus. And he has done so much good things in research, not only for the area, but for Starcy as well, in particular. Thilo, you're going to talk about the remains of metallurgy, modern copper smelting from the Trodos Mountains.
Thank you, Avi, very much for your very kind introduction. I'm certainly very happy to be here in Cyprus, even though I struggle to get out of this talk here and to find my own talk. So finish this here. Hooray. It works. Yes. So, welcome everybody again. It's a great pleasure, as I said, to be here and to be talking to you. Now, we have, as I mentioned yesterday, about 20-ish people in the physical audience, all of which are from Cyprus, and most of which have been here much, much longer than I have been here, so I don't need to introduce the Trodos Mountains. But considering that we have several hundred international YouTube visitors and viewers at the moment, allow me to briefly explain the title. If you look at the map of Cyprus, you will see here that central lump of rock. That is a Trodos. It goes actually up to 2,000 meters above sea level. You can do skiing there. That was the end of the commercial for the tourist board. But for the metallurgists, it's important to recognize that Cyprus, the word Cyprus, and the Latin word cuprum, which is the source for the element symbol Cu, and the word root for the English copper, it's all the same. And that's not a coincidence. Cyprus and copper are synonymous. Cyprus used to be the major copper source for quite a long time in this part of the world. But as I want to point out in my talk now, there is life beyond copper smelting. There's more to be for it to be done. But I should also point out the massive work that my dear colleague Lina Cassianidou has been doing on the primary production of copper in the Trodos Mountains and around the Trodos Mountains. So there's not much that I would need to add to it anyway. So when I talk about remains of metallurgy, what does that actually mean? What am I referring here to? There are three different types of remains. One is what's left behind the traces that go to the primary production. So that's the mining, the extraction of the rock from the mountain, and then the transformation of that rock, that ore, into metal, the smelting. And we need to recognize that this mining activity is a huge industry. It's pretty much an industrial landscape that underpins late Bronze Age and any later mining. There are hundreds and hundreds of people involved at any one time at any one major mine, and it happens both underground as in this 17th century picture from Austria, as well as above ground. There's a lot of activity going on in these mining landscapes. So there's a lot of work that can be done for economic studies and for environmental impact studies and all of that. In terms of what remains from it, well, a lot of negative features, speaking as an archaeologist, a lot of things that are no longer there, holes in the mountain. And a bit of the forest may still be there, but not much, because all of that industry is extremely wood hungry. An artist recently tried to visualize it sorry, by calculating the mass and the volume of copper metal extracted from a copper mine and projecting it back into that hole in the ground. And you see here that ball of copper represents all of that massive hole where it came from, which means something else has to came out of it. What is it? Where is that stuff? So there's a lot of slag being produced. This is an example of a slag heap from Cyprus, about 1 million tons of it from the Roman production period. Now the beautiful thing here, both with the mining and the smelting remains, is that that stuff is typically where it has been produced. It doesn't move far. Thank you, Kyriaki, that's extremely helpful. So, if you see a mine, if you see a slag heap, you know the activity wasn't far away, other than chronologically far away. And it's typically a single focus activity. All of that industry, these hundreds of people, were pretty single-minded. They are doing one thing and that's it. And that's pretty easy to figure out what they were doing. The interesting bit is to figure out how they were doing it, because that differs. That's culturally driven as much as technologically driven. And why did they do it? What motivated them? Were they coerced labor? Were they free enterprises? All of that. So there's a lot of research, but in terms of technicality, it's where it is. There's another main type of remains, which is the actual finished artifacts, which dominate our understanding of archaeometallurgy. The objects that have been produced from that copper, either as ingots, and again here's a Cypriot one, or as finished tools, weapons, jewelry, decorative items, you name it. And there's 100 years plus worth of research tradition here, so we know what to do with that. We identify chemical composition. We look for provenance. Where does the object, where does the copper come from? Because these objects do travel. That makes them interesting. If we look at the ingot, we have them mostly from shipwrecks. They're not used on board a ship. They're just carried around and then sunk with the ship. So that's where we find them. Clearly not near the production. All these objects, move to where I want you, thank you. These objects easily travel long distances. Eventually they are being either lost or buried with somebody, but not again where they were made. You can look at the objects to study how they were made, and there's a lot of metallography and research, but I'm not going to talk about that. As I said, that's well established, and there are good colleagues in this country and beyond who do that. What I want to focus on is a step in between the primary production and the production of the artifact. This secondary working, both hot and cold, leaves a lot of traces. Now, where does that take place? Where are people situated who take a piece of raw copper from the mine, from the smelter, and modify it into a useful object. That activity, now the answer depends on where you are and when you are, but most cases that happens not up in the mountains or in the cemetery, that happens in a settlement, in an urban context where you have workshops, where you live, where you may have a market, where you have your customers, your clients, and so on. If you're in a Roman period, it could be in a villa or in any other place where people are. And what were they actually doing? Now, the range of activities here is much more diverse than that single-focused production or deposition act. There are so many different things you can do to get from A to B, and it's quite interesting to figure out how they did things and what exactly they were doing in those settlements, in those workshops. And they can combine different elements, they can separate different metals, they can, as I said, both hot and cold work, they can recycle, they can repair, they can mass produce or individual single object production. So in studying these workshop remains, we are looking at activity reconstruction as a direct entry into the brain, into the activity of our ancestors, of the people whose residues, whose remains we are excavating. And often we get quite surprising answers, things that we didn't expect. And we get a lot of spatial organization here from that particular workshop. Now, to illustrate that, just a little example from a local site here, Hala Sultanteke, near Larnaca on the southern central coast of Cyprus, excavated extensively, a late Bronze Age important city, lots of metallurgy, but on the harbor. And there, besides lots and lots of slag, current excavations have excavated 100 kilograms of slag, old excavations, similar quantities. We have these tuyères. Now, a tuyère is a blowpipe to blow air into a furnace, into a fire, to control the airflow, to facilitate whatever metallurgy you want to do. Lina Cassianidou, mentioned earlier, has found similar tuyères in her smelting site in Politico Forades, and they are known from all over the world anyway. They consist of a body of red baked ceramic, clay, and then they have a small opening here on the one side where the air comes out, and a bigger opening at the back end where you blow it in with a pair of bellows, typically. So you have a very forced, pointed draft pointing into your fire. And typically there's a little bit of brown, black burnt area here on the working end. Now that is the part that we are interested in, because that shows what actually were you processing here. Yes, we know it's metallurgy. Nobody else would use these tools, but what type of metallurgy? Could be melting, could be smelting, could be copper, could be gold, could be silver. So how to do that? We have our portable X-ray fluorescence instrument with a very tiny spot that we can point onto various areas of interest. And in order to see which metals, we were looking at the top black part here to see the contamination that may have come from the site, from the charge in the furnace or crucible, and compare that to the back, the cold end, the red ceramic, where there is supposedly no contamination. But being in Cyprus, the clay here has automatically a little bit of copper in it, enough to be detected by it's a very sensitive instrument, so we need to get that threshold level and then see what comes above that threshold on the working nose. And that's what we did. And we see in red the spectrum of the normal ceramic Forget that central bit, that's an artificial peak couple from the instrument. But we see here a lot of iron, the red peak, the 2 peaks is iron. And in green, we plotted the analysis from that blackened, slaggy nose of the tuyere. And there you see a massive increase in copper and zinc. It goes way beyond the roof. That second peak here is only 10% of the intensity of the first one. You can see how high the copper peak goes. And we have a tin peak with its second here. Now, tin you would not expect in copper smelting from Cyprus because the copper ore simply doesn't have tin, but it's obviously the main component of bronze besides copper. So here we suddenly have, quite unexpectedly, strong evidence that these people were using tuyeres to melt bronze. Now, it's not that unexpectedly, actually, because we are in a settlement after all. The unexpected thing is still what are these hundreds of kilograms of smelting slag doing here, but that's a different story. I just want to use this as an example how with no sampling, no effort, it's a work of an afternoon, if you know exactly what you do, to discover, okay, these tuyeres, they are not linked to the smelting slag, they are not like the ones in the mountains, these are from a different workshop. So that's the kind of things one can easily do to clarify what activity took place here. Now, I won't bore you with crucibles. I have spent 30 years of my life studying crucibles and published far too little or far too much on it, however you see it. But they are clearly part of what I'm interested in. However, the problem here is crucibles are, again, movable. And I asked Tom Brogan yesterday about their crucibles from Crete. Yes, he had them, but not in the workshop. They had been moved around in the settlement. So yes, if you find crucibles, you can see there was a metallurgist somewhere and you can see what they were doing, but you don't know exactly where, other than that somewhere in the vicinity. So what I would like to introduce you to now is a concept of micro remains, which picks up on the work we heard yesterday on archaeobotany and tiny bones and stuff like that. So what we are doing here is to look at the traces left in the soil. And some 6-8 years ago, Chris Carey and friends rebuilt, they used a rebuilt Iron Age hut in Britain and rented it for a weekend and did a lot of experimental work there in this, within that building. And note, it's a thatched roof, but you can easily do metallurgy inside. It won't burn down. You can do metallurgy at home. Maybe not today with health and safety, but in typical normal circumstances you can. And what they did, they mapped the footprint of the hut, and then they had activity areas. In this shaded area here, that says copper casting 15 times. Here it says sweeping the dirt out of the hut in front of the building and doing some cold working. And then some other 3 times here and 5 times something casting there. I can't read the small print, but it's in the paper. And you see all these regular dots, 50 centimeter interval, that's where you then take a sample and analyze the soil after that weekend of activity. And you plot the concentrations, in this case of copper. The green is base level, and the more yellow and the more red it gets, and the brighter, the higher is the copper content. And you see where there was the 15 times bronze casting, there you have a lot of dirt scattered around in the soil. And yes, there were good, clean people, and they were sweeping the workshop every now and then, and that's where you collect also a lot of your copper debris. Now, that was an experimental study, and we know that copper dissolves over time and migrates in the rain and in the groundwater. So how long does it actually show up such a signature? That's where my friends from China come in, Xiran Liu and Chen Zhanli and others, on a 13th century BC Bronze Age site in China, where they plotted the same copper content, same signature, the more bright, the more copper, and found in that particular longhouse here areas very rich in copper. And then they took samples selectively in those areas and washed the sand, washed the soil. And that's what they found with wet sieving. This is a centimeter, each of these squares. A lot of tiny bits and pieces you wouldn't pick out if you excavate. They're not green, they're just dirty. But if you wash them and mount them, this whole block is 2 centimeter diameter. You see these tiny fragments of slag, millimeter-sized slag, and lots of them, and copper and bronze and all sorts of stuff. In short, through the study of a handful of those polished blocks, we were able to discern different activities in different parts of the site. Here they were alloying, mixing copper and tin. There they were recycling, doing something else, different type of waste material, something that was not visible at all from the surface. So the important bit is to look for the invisible, to know what you're looking for, and that you can do in a lot of excavation situations. And to ask somebody to come with the handheld XRF and zap your soil while you excavate, it's very easy. And it can give you an early warning, oh, we may wish to do something more careful here before we remove the soil, because then it's too late. So this secondary copper metallurgy leaves a lot of less visible remains, not just mold and crucibles and offcuts of metal. And typically it's on less than ideal sites for archaeological purposes. I mean, somewhere in the middle of a town when you have a building site going on, developer driven, and you suddenly excavate something, you don't have a long lead-in time to plan your research carefully. That's where the rapid response of a handheld XRF or a portable laboratory, as Sorin demonstrated earlier, can be really helpful. And it's sufficient, the quality of the XRF, the handheld, just to see high copper, low copper. You don't need to quantify in absolute terms here, but you can map, again, in a matter of hours, you can map a large area quite significantly. And then you can do your targeted soil sample rescue excavations, bagging it for later processing in the lab. So that was one bit. Now, speaking of Cyprus now, and I have another 10 minutes, I hope, having started a little bit late. Thank you, Evie, very kind of you. I would like to flag up one thing that's missing in Cyprus. I love the country dearly, but something is missing, and that's iron. In the archaeological record, I mean. Now, we have a lot of Iron Age and very important Iron Age sites across Cyprus, and of course we have a lot of nice Iron Age iron objects, obeloys, spits, lots and lots of them, very highly valued, some of them inscribed with Cyprominoan script and whatnot. The problem with that iron metal is it can travel. You don't know where it comes from. And if you look at it more carefully in color, and if they allow you to cut through it, actually there's not that much iron left. It's mostly rust. So yes, it's nice to have these objects, but what does it tell you about who made them, where were they made, how were they made? That information you don't get typically from the finished object from a cemetery. What's missing is the iron slag, the waste from working, making, processing iron. And that can't be really missing. It's more likely that we just don't see it, because nobody is cleaning the whole island thoroughly of all the iron working debris produced in 3,000 years. It must be somewhere. Now, that piece of slag here is not from Cyprus. It's from Ethiopia. But it just serves as an example to show what can be done with a single piece of 5 centimeter worth of slag that came from a town next to a mining area where we don't know yet what Actually, they were mining. That's an ongoing research project. And there were no iron objects, but just a few slag finds. So what is this slag doing? Was the question by the archaeologist, slicing it open. And I'm grateful to Brunella here for doing that work for me. You see a microstructure like that. That is 0.05 millimeters. The bright stuff is iron metal. The egg-shaped or grayish orangey color is iron oxide wüstite, a typical slag, iron smelting slag face. And you see a lot of this more bluish corroded iron metal. So in fact, there was much more iron metal here than it looks like. This is a typical example of a semi-finished bloom, a product from primary iron smelting, just badly corroded. And when you corrode your material, your iron, it forms a crust around your object, as all conservators know very well. And that crust traps some of the soil, some of the sediment within which the object is corroding, and therefore preserves some of that environmental context, which in this particular case has the typical quartz particles of sand, a lot of the the grayish iron hydroxide filling porosity, more or less. And in this particular sample, there were a handful of these very long, thin, orangey-looking slices of something. So, what do we make of this piece now? It clearly tells us somebody was smelting iron in this town. We don't have the exact context, but nobody would carry that slag from A to B. It's bound to be very local. Maybe you throw it after your goat, and then how far can you throw? That's how far it may have moved, but that's about it. So it shows a local activity, and it shows that these people were actually skilled in making iron metal. But that is not what you need. You need somebody who makes a tool out of your iron metal, and that is what a smith is doing, and a smith is not a smelter. A smith is somebody who knows how to work the metal into an object, as opposed to somebody who takes a stone and makes metal from it. Different activity and a different product of waste. A very typical example here, a cross-section through a smithing hearth bottom, a plano-convex. It's about the size of my hand, a very typical shape, and you cut it in half and you see that typical texture. That is what you would expect in a smithy. For some reason, we don't see that, even though in many other countries we have kilograms and kilograms of smithing slag around the smithy. The smith keeps their workplace clean, but they don't throw it away too far. What does a smith's workplace look like? Here's an example of a sub-recent one. You need a stone, an anvil, and that's it. Well, and a hearth, charcoal to make fire, and that's it. So in terms of infrastructure, it doesn't need to leave much. You can even do it on a wooden stump, as Peter Crewe did in Wales 20 years ago. That leaves even less. Even though you have red-hot iron here on that wooden stump, no problem. You burn a hole into it, but so what? And then you see how they are smithing it, and the sparks are flying all over the place. If you look at the Roman examples, smithing is almost a seated affair, it seems, an office job. You can sit here on your stool, you have a raised hearth where you hammer, you have a chap who pumps a bellow for you in that raised hearth. What do you find of that once the surface has been raised to the ground? So it's not a surprise that we don't see much in terms of installation here. But what happens during smithing, actually? Look at this piece of white-hot iron, already bent back on itself in the process of being smithed. In the next picture, we will get the hammer blow coming from the top. And I should credit David Dungworth here for the fascinating movie from which I stole the stills here. You see just about the hammer head here hitting that piece of iron, and you see the sparks flying in all directions. What are sparks? What is a spark? It must be some substance. It's not a light ray, it's not a photon, it's a particle, a red-hot glowing particle being sprayed out from the surface of the soft iron, being tiny bits of iron metal burning in mid-air as they fly with the oxygen of the air, therefore giving that spark, changing into iron oxide. And that whole sequence was a split second. It's a high-speed movie that he produced here. But you see the vast number of particles that come out from a single hammer blow. And that is the type of particles when they are cold and cool after the process, hammer scale. And at the end of the workday, around your anvil, you have a gray layer in the soil of that stuff. This hammer scale, it's tiny, it's fragments of a millimeter. Yes, you can sweep your floor and try to keep it clean, but inevitably will trample quite a bit of it into your soil. And it has a very diagnostic shape, and it's a mineral form called magnetite, because it's magnetic. And that piece of hammer scale here and the other 5 in that sample demonstrate that this particular slag piece, yes, it's a local smelting slag, but they were also smithing in that particular workshop, because no other way would produce that piece of hammer scale. So what can we do with that? We can lay a grid over our excavation, 25 by 25 centimeter, find a volunteer and a handheld magnet. And the magnet you get from whatever shop in the supermarket where you buy to pin notes on your fridge or on your magnetic whiteboard and so on. And then square after square, you go slowly over the dry soil and you pull out the magnetite, the hammer scale, and you weigh the quantity you pull out per square of those tiny flakes. And then you map it, and you have your activity focused squarely and firmly here in the surface area, in the first layer, in the second layer of the excavation. You know exactly where your anvil was, because that is where the hammer scale is scattered around. So again, we are making the invisible visible with limited effort, other than the poor volunteer on her knees, spending a few days mapping that. But we can pinpoint here was a smithy. No other remains would be able to do that. So these secondary metallurgy remains have a massive research potential, much of which remains unexplored, and a lot of which is really low key in terms of instruments. Bronze working, alloying, recycling can all be easily identified. 3,000 years of iron metallurgy in Cyprus, entirely missing. It must be somewhere. And if my dear friends and colleagues from the DOA or the foreign missions find some suspicious iron slag, let me know. And then there's silver and lead and gold and all of that. So there's much more still to be done. Lots of different metals. The tools we have in place here at the Cyprus Institute and elsewhere, the Archaeological Research Unit has a similar one, and we are happily collaborating. And we have this nice scanning electron microscope, which Maria already flagged up as an absolutely essential tool if you want to do more in-depth analyses. It's dedicated for archaeological science research. It's hosted at the Cyprus Institute. It's partly supported by the A.G. Leventis Foundation, where I'm very proud to have the named chair of the A.G. Leventis Chair of Archaeological Science at the Cyprus Institute. And we are funded also by the European Union Promised project, and I thank you for your attention.
Thank you, Thilo. That was brilliant. Questions? Well, he's good, but he's not that good. You have to ask something. You understood everything. Caroline, online questions? I'll make
Make it up.
No, I'm not going to make it up. It's very fascinating what you said about the secondary metallurgy, because at Keros, and of course the material there, the metallurgy there is studied by our great colleague Maria Dikomitou, and of course she knows much more about it. But what I wanted to say of how you make the invisible visible, because we had at Keros so extensive recovery techniques, we have picked up all the small slugs. So they're everywhere. And there we have to thank the people that they did the flotation, but also the people that they did the sorting of the residues, and Carl Henkel in particular. And we found everything, all these small bits of slag. And we have problems comparing it with other sites, because nobody else had, the previous excavations didn't have such extensive recovery programs. And we are puzzled what does it mean, because we find small slugs everywhere. And what I wanted your opinion about is that, okay, it is secondary metallurgy, fine, but are there taphonomic processes that they go everywhere? Because we don't have like workshops in every place, but still, wherever we dig, we find these small pieces.
Now, that's a very, very important consideration and question, obviously. Being as tiny as they are, they do move quite happily. With any animal burrowing, with any soil movement that you do, whether you level workshop floor and redistribute it in the site or not. So yes, it moves around. That's why it's important to do this mapping to see where are concentrations. And that was also something in that Chinese site, very well excavated, research excavation, no settlement on top. They found exactly slag everywhere as a background scatter. But then they have these hot spots in the trench surrounding that settlement. There was one area where they obviously dumped the waste. Not the workshop, but in the mud of the moat. And in other areas, we saw it, oh, here there must have been the actual activity. But the important thing also is, people like myself, we need to listen and learn to archaeobotanists who float and who wash and who sieve and share that installation and work together and see, okay, yes, you find stuff that is black but not charred and you throw it away because it doesn't float. No, give it to me. And then we can actually maximize information output. And this collaboration, having different specialists working together and being based in the same institution, rather than one in Cambridge and one in South Africa and one in Timbuktu, where they hardly can communicate, that makes a big difference also to the quality of the work.
We have an online question now. So people are asking reference, like for experimental works. There is Amine Mami, which asks, is there any arsenic in the copper here?
Very good question. So the reference for the paper by Chris Carey and friends on the experimental roundhouse in Britain is Journal of Archaeological Science, I believe 2014, should be volume 49. I don't remember the page numbers now. I'm sorry. And the work that I did with my Chinese friends is in 2020, I believe, also Journal Archaeological Science. That is anyway, should be on my academia page. If not, I will put it up tonight. So in terms of arsenic, yes, actually, the student who helped us with that XRF work on Hala Sultan Tekke on those tuyères is in the room, and she may remember that on another tuyère tip, we found lead and arsenic and tin, as well as copper. And that is a little bit more interesting. Now, the arsenic could well come from the Limassol forest mineralization, where we know that there's a Cypriot copper with arsenic. The lead is a real surprising bit, because textbook wisdom has it, as far as I understand at least, there isn't much lead in Cypriot copper ore. So that would indicate, again, processing of imported copper. Now, we know from the analysis of artifacts that Andreas Charalambous and others are doing at the research unit from Lapithos, for instance, that there's lots of imported copper in the late Bronze Age, copper alloy in the late Bronze Age in Cyprus. So it's not a surprise. It's just another piece to the puzzle that we find here.
Thanks. And there is a... Do we have time? Yeah.
Yes. Yeah.
There is one more question from Manuel Peters, which asks, do you have any experience with the in-site environmental mapping spatial analysis with copper corrosion product instead of copper prills, hammer scale beside XRF?
Can you kindly repeat the question?
Do you have any experience with the in-site environmental mapping spatial analysis with copper corrosion product instead of copper prills, hammer scale beside XRF?
Yes, so what you actually map and the spatial distribution you do in the soil is mostly the copper corrosion, because that is what survives from the tiny bits of copper metal. Rarely is the copper still metallic there, and the copper corrosion products float around in the soil. That, I think, the best way initially is with XRF, but then for a more targeted, you can do soil sample and leach the soil with differently aggressive acids to extract whatever copper, zinc, lead, arsenic, bismuth, antimony, silver are there for a much more detailed analysis following a particular, well, there are different protocols, how to leach that out and analyze it. So a wet chemistry method is certainly helpful there as well, just that much more effort. And for the hammer scale, I would still very much recommend the magnet. It costs €2 and is the tool to use and doesn't wear out, doesn't need electricity, doesn't break, and is very selective. Now you can take it to the beach, sand, and pick up natural magnetite, but that you can see in the shape then under the binocular microscope. The hammer scale should be platy, and natural magnetite is not platy, it's cubic.
Okay, thank you, Thilo. You see, that's why we like him, because he remembers everything when it comes to science. For the rest, not so much, but okay, we can deal with it.
Sorry, what's your name?
Exactly. This is my piece of paper. Thank you. Thanks. So we're moving to Belgium now, and it's the last lecture of the morning session. Angelos, are we ready with Frederik? Let's see. Okay. Yes, okay. Oh, there we are. Is he online? Okay. Can he hear? Can he listen to me? Can he hear me, or not? Anyway, hello, Frederik.
Hello, Evie.
Hello.
Can you hear and see me?
Yes, very good to see you. And Frederik he's in Leuven at the moment. And he has done a lot of work on crucibles that we're very interested in Cyprus as well. And today he's going to talk about methodologies for the analysis of copper alloys and their production waste, from the field to the lab. Thank you, Frederik.
Thank you. Okay, so I hope you can see my screen. And if at any point there's a technical problem because I haven't used this software before, please do interrupt me. So thank you for the invitation to speak here. Sadly, I'm not able to join you in Cyprus today, but so I'm presenting this talk to you from home in Belgium. And so today I will be talking about copper alloys, starting with what are copper alloys, and then going into the kind of remains that we find. And so I think I'll be latching on to what Thilo has been saying. I hope and I think it will be quite complementary to what Thilo has just been discussing, and then go into sort of the general research questions that we have for copper alloys, and then how we can work these out in practice on site, and also taking samples and analyzing these further off site. And so copper alloys obviously start from copper, and copper itself is one of the first metals that people have started working with in the past, and it's also one of the few that occur in its native form in nature. That means that it occurs as a metal in nature. And it seems that this is also the first type of copper that people started experimenting with, and which we find in small objects, the earliest objects in copper at certain sites. But so the actual onset of copper metallurgy in its true form is when we start extracting copper from minerals. And these minerals are copper ores, which are very rich in the element copper, and which we extract in a metallurgical process called smelting. And from then on, once people start doing that, we really see copper metallurgy taking off. And it's actually also quite soon after that that we see the first copper alloys appearing. So for example, if we look at these objects from Egypt, very early on, as soon as we have the first copper objects, we also see the appearance of arsenical copper. And that is a first copper alloy, which we see appearing in the early Bronze Age at many different sites across the ancient world. And that remains popular for several centuries, even millennia. And so it has a slightly different color, as you can see on the left image. I'm not sure if my mouse is visible. Let me see if I can. No, I don't really see a tool for that. But so on the left, you can see a more yellowish appearance. But typically what we will find on site will be a corroded object, as you can see on the right. So it won't be possible to really tell from the start whether we're dealing with a specific type of alloy. But so arsenical copper or arsenical bronze is a first type of alloy we frequently encounter. Second one is bronze, tin bronze, which often is simply called bronze, but so stands for an alloy of copper and tin, which appears a bit later in the archaeological record, appears alongside arsenical copper, and typically starts to replace it gradually over time. And so this is an alloy of copper with tin, and often at a certain point in time in different places, lead is being added into that alloy as well, at which point we could call it a leaded bronze. But often in literature, we will see that it's still referred to simply as bronze. So bronze can cover as a term many different meanings. It can refer to an arsenical copper, to a tin bronze, or even a leaded tin bronze. And this is not always distinguished between very carefully. Another common alloy is brass, and this is an alloy that typically appears during the Roman period, where it's frequently used. And here's an example from 9th century Germany. So brass is an alloy of copper with zinc, which has a much more yellowish appearance than arsenical copper or tin bronze. And then as a final example, we have complex alloys consisting of a mixture of copper with different elements such as arsenic and antimony, but also nickel, silver, bismuth, you name it. And that actually is something we see quite early on in the archaeological record as well. The example I show here is from the Nahal Mishmar hoard in the Levant, which is a very early example of different alloys being exploited to achieve different colors, etc., which you can see here. And that's a specific type of copper alloy as well. So why do we see these copper alloys in the archaeological record? Where there's a multitude of reasons why people might start making these alloys. One could be that a mixture of copper with another element lowers the melting temperature of your metal. So if you're trying to melt a pure copper, for example, to cast an object, you need to reach a high temperature, and once you cast it, it will cool down and it will freeze quite quickly, which means casting a pure copper object can be quite complicated. If you add in arsenic or tin or lead, you have a bit more leeway to cast your object. It will also affect the hardness. So if you add a few percentages or even just 1% of arsenic, you will get a harder alloy, which will react differently to working. It changes the color, as we've mentioned earlier, so you can play with the amount of alloy constituent you add, and that will change your color from a reddish copper to a more yellowy, more golden, or a more silvery color, depending on which element you add. And it also changes the properties, not just perceived by the end users of the metal, but also by the metal workers themselves. And this is also another perspective which is being researched. So the type of copper as a sort of category in terms of working for a metallurgist. But there's overall a large variety of properties that are affected by the composition of an alloy. I won't read them all out loud here, but what's important is that we can look at these properties, but we need to see that they are part of a value system, part of a culture. And so the selection for a particular copper alloy is something we need to see as embedded within a particular culture, a particular society. And so any sort of discussion on how intentional the choice for an alloy is needs to be regarded from that perspective. So how are copper alloys made? So there's two main ways by which an alloy can be made. The first one is through the actual primary metallurgy step. So directly through the smelting of a copper ore, which not only has copper, but also other elements in it. And this is probably a less common way, but and I will spend a bit less time on it here today. The most common way is in a secondary process, when we already have raw copper and we mix that with an alloy component. And that can be a metal, another metal, for example, tin, or it can be a mineral, which is mixed together with your copper in order to get the alloy. That's a sort of primary mixing, obviously, and sort of active mixing. Obviously, the recycling of existing alloys, possibly with the addition of some other ingredients, is also important in this production, in this secondary step. But so the first type of alloy production is through smelting, and in that case we're talking about these complex minerals. So you have a variety of minerals which, apart from copper, also have high concentrations of other elements such as arsenic, antimony, tin, etc. And when we smelt these, when we process these in a furnace through one or more steps, which we won't go into here, we can have a process called co-smelting, which refers to the fact that not only your copper is being extracted, but also another element. And so we end up with a raw copper alloy in a certain form, could be an ingot or something else, and a slag or a waste product. And so from that raw copper alloy, then objects can be made, and objects such as those we see in the Nahal Mishmar hoard, but also others, for example, made in Anatolia, in the Alpine region, or in Italy, appear to have been made through this kind of process. But so it's a specific type of alloy, and what I want to focus on a bit more today is the most common way of making alloys through a secondary alloying step. And so here we depart from our copper ore. We have a primary smelting step to produce raw metal, and then in a secondary step, the alloy component, in this example tin, is added, usually in a crucible, mixed, and from there an artifact can be made. And so this is, as Thilo already mentioned, something we typically encounter in urban environments, in workshops, and these can vary very much in scale. So this can be small scale, household type production at low frequency, up to very large industrial scale workshops. So there's a very big variety in that sense. And so the most important material culture associated with this is a crucible, which is the ceramic vessel which we use to mix and melt the metals. And these ceramic vessels are quite particular in the sense that they need to be able to withstand high temperatures as well as the corrosive action of your metal charge. And then these are heated in some sort of heating installation. And as Thilo already mentioned, this can be quite limited, ephemeral. You don't necessarily find a furnace in which a crucible was heated. And then, as mentioned as well, these crucibles can move. But so the crucibles themselves hold a lot of information concerning what the alloying process was. And so they come in a large variety of shapes and sizes. These are a reflection, on the one hand, of the process for which they are being used, but on the other hand, also a reflection of local traditions feeding into ceramic technology. And so they are worth studying from a typological perspective in their own right. Here, we will use them as an instrument to understand the metallurgical alloy production process itself. So these crucibles are used for the alloying, but in many cases, they're also used for the casting process. And so that casting is pouring the liquid alloy into a particular shape by using a mold. Now, molds are something which we find even less frequently than crucibles, because molds tend to be broken to free the object we've just cast. And in many cases, they're made of a ceramic which isn't fired to a very high temperature. So this is a kind of object that we need to be careful in retrieving. It doesn't necessarily look like anything. It could be a non-diagnostic piece of ceramic, low fired. If we are lucky, like we were here on the right-hand side in Gordon in Turkey, you will find the interior, the interaction phase between the ceramic and the metal, which typically has a darker color, and using a handheld XRF will still show traces of the contact with the metal. So it is definitely worth looking out for these small fragments of kind of weird looking but heat impacted ceramics. And then there's a variety of secondary steps, cold working, hot working, annealing, hammering, which in and of themselves don't necessarily leave a lot of traces, except for, as Thilo just discussed, the tiny micro fragments which will end up in your workshop. But the bigger tools are not necessarily going to be left in place. So what do we expect to find in a workshop context? Crucibles, although in many cases they will be thrown out of a workshop, so they will be perhaps in the surrounding, in a dump area surrounding a workshop. The same for molds. Furnaces, perhaps unlikely. Tuyères, which are the, as Thilo mentioned, the ends, ceramic ends through which air is blown into a furnace. And on this illustration, you can see the boy sitting on the left blowing air through bellows through a tuyère into a furnace. The bellows typically are made of organic materials, so we usually don't find them. But the tuyères sometimes we do find. And then ash and charcoal, a very important part of the workshop remains, which is perhaps more likely to be left in the soil and something we can find through micromorphological analysis of a workshop soil. Same for the casting spills, which when you cast the bronze, typically some of it will miss the mold, end up in on your floor, in your soil. And large fragments will be picked up for recycling, but tiny fragments will remain in your workshop contexts. And in some cases, we will also find ore minerals. So these are the kinds of materials we expect to find or hope to find in or surrounding a workshop context. And then obviously, there are the copper alloy artifacts themselves, which hold a lot of information, but which we expect to find in a variety of either use or a deposition context, such as a funerary context. And so the main questions we want to ask of copper alloys are, on the one hand, technology, roughly speaking, how was something made? And obviously, why was it made that way? And then provenance, where was it made? Where did the materials come from that were used to make the object? And why did they come from that particular location? And obviously this distinction between technology and provenance question is kind of artificial because those two questions feed into each other. And so we really need to integrate them in our research, but we can sort of separate them in terms of how we approach them analytically up to a certain extent. And for the sake of having a more clear presentation here, I will treat them one by one in this case. So we will start off by looking at technology, where we're trying to look at the choices people made in the past, how certain ideas, technological ideas developed and were transmitted, how a production was organized in a society, etc. And so we can approach this on the one hand through artifacts by looking at their composition. So for example, how high is the concentration of arsenic, tin, etc.? What kind of alloy do we have? And we can look at the artifacts microstructure to determine whether they were cast, whether they were worked in a secondary way, etc. So those are things we can analyze from the artifacts themselves. However, it's also the production remains which are very interesting, and in some cases perhaps more interesting because they allow us to look at the process itself from the perspective of technical ceramics, such as crucibles, and where we look at the microstructure, and again, also elemental analysis, and also by looking at the broader context. So looking at the where we find them and the materials that we find associated with them. So in practice, what do we do when we excavate a workshop context? Obviously, a detailed recording of the spatial deposition of these different finds, which I've mentioned. And we need to document and conserve them, as I suppose you would do with any kind of material culture you encounter on the site. So it's important to photograph, draw these kinds of materials, and also to establish a typology for things such as crucibles and tuyères. And as mentioned earlier, it's important to perform sieving, so we can capture these small fragments of charcoal, of spills and other fine materials. And for example, to look at charcoal fragments, which can tell us something about the kind of fuel that was being used in metallurgy on the site. And also important not to necessarily clean your metals because the corrosion on a copper alloy acts as a stabilizing agent. And in terms of ceramics, molds can be quite fragile, and you might remove the contact surface. So a high-fired crucible, not such a big problem to clean, but the more fragile ones, you should be quite careful. And so this is an example of a field setup we had in Egypt almost 2 years ago now, where on the left we were sorting out the different kind of workshop materials coming out of the excavation. And then in the back you can see portable XRF, which we use to identify the kind of copper or copper alloy in the finds, or which were slag, crucible, etc. And then we measured these, drew these, and took pictures of these, including for some particular objects 3D photogrammetry. But so the handle XRF is a very useful tool in this sense. On the right, you can see the mapping of features within a workshop. So that allows you to see where there's a contamination of copper and where there isn't. And so to really map the activity within a workshop. And on the left, we can also use it for the analysis of artifacts as well as crucibles, and that allows us to quite quickly identify the kind of copper alloys that were being processed in a workshop. Now, if we want to go further and we want to know a bit in more detail what an alloying technology looked like, we need to sample the artifacts, and I will focus here on crucibles and artifacts. And so for a crucible, we typically need a sample of a centimeter up to a few centimeters, preferably towards the bottom of the crucible itself. And that we can then embed in resin and look at under the microscope and the scanning electron microscope. So those are the two powerful tools for us to really understand what's going on inside a crucible. And so what we will do then is look at the different contaminations, residues that are trapped in the interior surface of a crucible, which is often vitrified, and so we'll capture residues of the process. And that will allow us to find out what ingredients were used, whether we're dealing with alloying, recycling, what the process parameters were, and also to look at the ceramic technology. So the handheld XRF allows us to identify a broad range of processes, and then going to the lab, we can go into more detail on these processes. Same for copper alloy artifacts. We can identify the alloy of the artifact. Despite the corrosion on the surface, we can get an ID. But if we want to know a bit more, we can take a sample, which allows us to look at the microstructure under the microscope. And then from there, look at forming methods, whether an object was cast, whether it was worked, what the hardness is, how the corrosion developed, etc. And so in terms of sampling in the field, as I mentioned, it's important to first photograph and draw the sample before taking the artifact before taking a sample, and then to not alter the microstructure of the material when sampling, and also to record where we are taking a sample. And so for crucibles and metal objects, you can use a saw, a fine hacksaw, a rotary tool, kind of a Dremel tool to take a sample. And this is something you preferably discuss either with your colleagues on site, what could be a good location to sample, or with the specialists with whom you're collaborating for the future study. So talk first, sample later, because once you've taken a sample, obviously you've altered the integrity of your artifact. So that's what we can do in the lab for metals and crucibles. So we make use of microscopy, SEM-EDS, and XRF, which we can also do in the field. So that's concerning technology. In terms of provenance, which is the second part of our main research questions, we can look at the geological origin of our copper, of our metal. So we're making a reference to where it was being mined, at least the copper part. But we can also discuss provenance in terms of production origins, which is in some cases perhaps even more interesting. So we can look at the production unit, a workshop, as a point of reference for provenance and for a discussion of how metal was traded, exchanged, and a more broader discussion of metal economy in a particular society. And so the main tools we use for provenance research are trace element analysis and lead isotope analysis. And this is something we tend to perform primarily on artifacts, although not exclusively, and I think focus on the smaller finds is proving to be very valuable for provenance research as well. And so here on the right, you can see some examples of a study we did on a workshop in Egypt, where we analyzed a range of artifacts, some of them scrap, which was ready for being recycled in a workshop. And then on the top right, you can also see a range of small finds, fragments, bits and pieces, which we would categorize as production remains, also casting spills. And so we can perform the same type of analyses for these kinds of materials. We can do the same for crucibles, but that's a more complicated story. So I will stick to the metal here. Now, sampling a metal artifact, we follow the same considerations as previously, but for a provenance analysis, we need a much smaller sample. So you don't need as much material. In case you're dealing with, let's say, a flat artifact or a small artifact, you can clip a small sample using either a saw or pliers. But as you can see here on the right-hand side, you can also use a steel drill to make a small hole. And on the right, you can see the object before and after, and you can see the small 1 millimeter drill hole, which is invasive but limited invasive, and which you can then fill up with wax quite easily to prevent further corrosion post-sampling. Again, something you should discuss, obviously, with your colleagues and the specialists you're collaborating with. And on the right-hand top, you can see a kind of artifact, in which case we decided to sample with a clipping. On the bottom right, you can see the kind of shavings you get when you use a drill. So obviously, you only need about 0.1 gram of materials, which can be a lot depending on the size of the artifact, of course. And it can in fact be less, but that again depends on the lead concentration of your artifact. So something to discuss. So these samples we take to the lab, and this is an example of the lab we work in collaboration with the University of Ghent. And so we dissolve our metal sample in acid, gives you these nice blue solutions, as you can see on the left. And part of this we use for elemental analysis, and another part we take to these ultra clean labs, and we extract lead for lead isotope analysis. And so these are the kinds of instrument we use. So an ICP-OES, this is the type of instrument we have in Leuven for elemental analysis. And so it gives you a full suite of the element composition, main elements, your copper, your alloy constituents, but also trace elements, which will tell you something more about provenance. So it goes a bit further than what we can do with, for example, XRF or SEM-EDS. We can also use ICP-MS, which has even lower detection limits, so we can look at even smaller concentrations of trace elements, but this isn't really necessary in all cases. We're often satisfied with the results we can get from ICP-OES. And then finally, we have a multi-collector ICP-MS, which is an even bigger beast of a machine, more sensitive, and it allows us to look at the concentrations of different isotopes of an element, and in this case, lead. And so why do we want to do this? Why do we want to analyze these trace elements and these lead isotopes? Well, for provenance analysis, we want to make a link between the ores, the raw metal, in this case copper, and the final copper alloy artifacts. And to do so, we make use of the geological nature of copper ores. So copper ore is a mineral that has a very high concentration of copper, but typically those minerals also have other elements within them in low concentrations. So things like silver, arsenic, cobalt, etc. And so when we produce an artifact, when it's being smelted, we have the ore with a certain trace element fingerprint, which is symbolized by a fingerprint here. And part of that will be carried through the smelting process. So on the top, we have the smelting process for copper, and we see that the fingerprint is maintained, but some elements don't behave the same way as copper, so we lose a few of them, or their concentrations can change. And the same for tin. And when we alloy, we get another change. But what we end up with as a trace element fingerprint on the right still has a relation to the original ore from which it was produced. And so we can use that to exclude possible ore provenances, although in many cases we won't be able to uniquely confirm an ore provenance. And so that's where the lead isotopes come in, and I will briefly explain what these are and how we use them. So lead is an element which has 4 naturally occurring isotopes, and an isotope is a variation in an element. Every isotope of lead is lead. It's chemically the same element, but it has a slightly different mass because it has a few extra neutrons in the nucleus of the element. And so since the beginning of the Earth, in geological terms, there has been a certain amount of lead and in its different isotopes. And over geological time, more lead has formed through the radioactive decay of uranium and thorium. And so as geological time has progressed, the lead isotope ratios in the mantle of the Earth have continued to change. And so they act as a sort of clock for geological time, which you can see here is sort of evolution of the lead isotope ratios within the Earth's mantle. And so when a magma comes out of the Earth and crystallizes at the surface to form a copper deposit, there will be a small amount of lead included within that deposit. And actually the process of changing over geological time is frozen. And so the lead isotope ratios in a copper deposit are a reflection of the geological time at which that deposit was formed. And so that will vary between different deposits across the Earth. Lucky for us, when you smelt copper from such a deposit, the lead isotopes are transmitted into the metal without changing. And so we can complement our trace element analysis with lead isotope analysis, which doesn't change through our primary smelting. And when we're dealing, for example, with a tin bronze, the lead in tin is so low that in the majority of cases, the lead isotope ratios of our copper alloy will be a reflection of the copper. Now, when we're dealing with other alloys, for example, when we're dealing with lead, that story will change, and I won't go into it here, but it allows us to look at, for example, the provenance of lead. But so this is the main idea. These are the tools we have that allow us to look at provenance, even though obviously, and there's been much debate, which I won't go into here, there are problems we need to take into account when interpreting these data. But so we have a much improved resolution. We can typically exclude certain provenances, look at the geological origin, but we can also model how the composition of trace elements, lead isotopes for metal in a particular society changes over time, and that allows us to evaluate whether the same sort of metal is being used over time or whether a stock from different places is coming in, whether metals are being imported, and so sort of model a metal economy on a larger scale. And so for that, as I said, we use this elemental analysis and lead isotope analysis. Now, what I want to finish off with is mentioning that what we try to do is to follow an integrated approach. So the study of copper alloys begins in the excavation and integrates an analytical protocol from the start. So it's, as mentioned before, important to, where possible, to contact a research institution that has access to a portable XRF. Use that for the mapping of your contexts. Yes, I'm wrapping up. Thank you. Finishing up, and so analyzing your workshop context itself and the features we find there, as well as the artifacts that are excavated. Photogrammetry is also a very valuable tool, and I think being used in any case more and more on excavation sites. But for example, here on the right, you can see an excavation we did in Sudan, where we have a very complex kind of feature, which in order to get sections at various places is very convenient to have a photogrammetric model. We take samples as well. So in this case, both crucibles and metal finds, which we're currently analyzing. And what I want to mention as another valuable tool, which I haven't gone into today, is experimental archaeology. So as Thilo already mentioned, experimentation can give us a valuable sort of reference guide on how to interpret features we encounter in archaeology. And in this case, we have rebuilt the kind of feature we found in situ, run various experiments and looked at the kind of deposits we get, for example, in terms of ash, small features, casting spills, etc. And also to understand how these things work. So on the bottom right, you can see myself and my colleague Georges Verly, who is an expert in experimental archaeology, conducting a casting experiment with the kind of feature we excavated. And so that really helps not only to understand what we excavate, but also to better excavate our workshop contexts. So to wrap up, there's a large variety of copper alloys in archaeology, and we can study them and their production remains to look at the technological choices that were made in the past. And so it's important to look at artifacts as well as production remains, as well as the contexts in which they were produced. And we can look at the provenance of copper, both in terms of raw materials, but also in terms of broader metal economies in which we incorporate recycling as well as trading, exchange, etc. over time. So that's it from me. I'm very happy to answer any questions you may have. Thank you.
Thank you for that very nice talk. We have a few minutes time for a few questions. Any volunteers? In the meantime, Frederik, you mentioned quite rightly that ideally for all these chemical analyses and lead isotopes, we want uncorroded metal drilled out of the sound body of the artifact. But I was wondering, and as you know, I'm trying to explore, how good is actually corrosion material to use, at least for the lead isotopes? Not for the trace elements, but for the lead isotopes. Is that, do you think, a feasible way, if we don't want to sample the object itself, to just make do with a corrosion that may be cleaned off or falling off anyway?
Well, I think that mainly depends on your burial environment. So, to my knowledge, there haven't been that many studies investigating this. But depending, if you have, for example, a dry burial environment with very limited movement of ions, then I wouldn't be afraid that there is a difference in your lead isotope composition for your corrosion surface versus your metal, your intact metal. If you, however, have a very wet, mobile environment, this can be affected. To which extent will depend on the lead concentration you have in your copper alloy to begin with versus the lead concentration you have in your environment. And so this will vary based on each situation and needs to be evaluated as such. I don't think there is a strict differentiation we can make, but in certain environments it is something you might need to worry about, that a corrosion might give you a skewed lead isotope composition.
Oh, no, but that's very helpful. Thank you.
We have an online question from Bart Cornelis. When analyzing a crucible chemically, would you get a result for the last use of the crucible or a mixed result of multiple use of the crucible?
Okay, so this is indeed a very interesting question. The reuse of crucibles is something that is often a bit maybe avoided or not really dealt with in depth, and I myself might be guilty of that. I try to, but so you can imagine different sort of situations. You can have a crucible that is used for a single purpose, let's say the melting or the alloying of a particular alloy once or several times. If that's the case, you don't really expect there to be a problem in terms of the results you find within your crucible. They will all reflect the same kind of process. On the other hand, we can find crucibles that have been used for a variety of processes. The question then is, how well have they been cleaned in between? And so, for example, if we look at more modern graphite type of crucibles, and we do that in our experimental workshop as well, you can clean them quite thoroughly after each casting, and there's not really anything sticking to them in the end. And so when we have these more dry crucibles, typically you will only see the last process. That being said, it's very well possible that you have residues and that you have a mixture of residues ending up in your crucibles from different processes. And the question then is, when you find these, to evaluate whether or not they make sense as a single process or as a reflection of multiple processes. But there's no sort of clear path on how to distinguish that.
Yes, and if I may add to that, there are also some examples where a crucible after use had been re-lined on the inside with a thin clay layer, burying basically the old dirt from the previous step and then providing a fresh surface. So then you can actually do your stratigraphy. Good. Any more questions? I think here at least it's time for lunch. Then let me thank you again, Frederik, for Skyping in and giving us this lecture. I'm sorry you couldn't be here in person, but better times will be ahead, and we look forward to welcoming you back to Cyprus. Thank you, everybody, for your patience so far, and see you in an hour again for the next round of lectures. Okay, we are ready? Thank you for being back, everybody. And I'm very happy and pleased to introduce now Professor Frederik Degryse for the next and first of the afternoon lectures today. Frederik is a geochemist and geologist by training, but has for a long time honed his skills as an archaeological scientist, very successfully dealing with, I think with everything more or less, ceramics and glass and metals and production and artifacts, provenancing, stable isotopes. And most importantly, he's a very good person, very good colleague to have, very pleasant to work with, and we are delighted to have him as a co-PI in our joint PROMISED project. And in that capacity, I'm welcoming him here now to give us a lecture and to tell us everything about the possibilities in the analysis of glass and vitreous materials, reviewing questions and answers based on his long experience. Frederik, over to you.
Thank you very much, Thilo. Too kind as usual. Thank you for the opportunity to speak at this workshop. Unfortunately, I cannot be there present in person due to the prevailing circumstances. A very wise decision to not allow Belgians in, but perhaps just in the nick of time to not be able to travel there. I hope you had an excellent lunch in very nice weather conditions in Cyprus. We'll be speaking about the possibilities in the analysis of glass and several other vitreous materials in a workshop that has as title the what, how, and why. Why would we do this to glass and other vitreous materials? And so we'll be speaking of glass as well as glaze and enamel in this presentation, but the focus will be on several kinds of glass. Just as a short reminder, glass is mainly silica. So the basic substance that makes a glass network is silica, and silica in the mineral form, pure silica, is quartz. And so you can find quartz in quartz sand or in quartz pebbles, in flint, and this substance is used to make the glass network. But this substance melts at a very high temperature, basically not achievable in ancient times, and so 1700 degrees is quite high. So you add a substance that would lower that melting point because it forms a chemical eutectic, and that is called a flux, a melting aid that will lower that melting point to about 1100 degrees centigrade. Now, for this flux, several raw materials have been used over time. The earliest one is plant ashes of halophytic plants, so plants that grow in a sodium-rich environment, usually the desert or the seashore. And there are several genera of this type of plant that when you burn them, you get an ash that is rich in sodium, but also potassium that acts as a flux. The second most known or well-known flux is natron, which is mineral sodium carbonate, which originates from Egyptian and possibly other North African lakes, and that you find in this sort of platy precipitate form on top of the lakes at the end of summer and the beginning of autumn, and that you can harvest, and that is nearly pure sodium carbonate that you can mix with silica to make a glass. And the big difference between this natron glass and this plant ash glass is the content mainly in potash and magnesium. Both of these glasses are soda lime silica glasses, so they contain a lot of silica, hence you have a glass. They contain lime as a stabilizer, otherwise this material would dissolve in water, which wouldn't be very useful. And you have a high content in soda, in sodium oxide soda, that acts as a flux. But the plant ash does contain significant amounts of potash and magnesia as well, while natron does not contain these substances. This mineral form of flux is much purer. Now, any glass will also contain a couple of % of other elements such as aluminium, iron, titanium, that you can naturally find in a glass. So the big difference between this plant ash glass and this natron glass is this potash and magnesia content. A third flux that is commonly used is, again, plant ashes, but now of tree ash. So you burn trees, which gives an ash mainly rich in potassium, and that you can mix with the silica to make a glass or a mixture that will melt into a glass at a lower melting point. And this tree ash flux from beech or oak or other plants such as bracken is found mostly, this production, in medieval Europe. Now, this gives an opportunity, these three major flux types, to do a sort of technological dating, because these three traditions of use of flux, to mix flux with a silica to make a glass, occur over time in different regions. And so this gives you a sort of opportunity to date by chemistry glass technologies. There's, of course, other constituents to glass as well. Copper cobalt has blue colorants, opacifiers, which make the glass non-translucent. Antimony is used before the 4th century CE, tin after the 4th century commonly. So these specific elements and element associations can give you information on the time period the glass was made in, next to, of course, typology and classical archaeological approaches to glass form. To give you an example, and this is very much the work of Ian Freestone, the Portland vase is a famous piece of ancient glass. Many copies were made of it, but the original in the British Museum is supposedly a Roman glass vessel. And it has a large history of breakages, the most famous, perhaps the first one, in 1845 involving a stone statue, a drunk student, which smashed this vase. And there are fragments of it. Every now and then this vase needs to be restored, re-glued, and so sometimes small pieces are kept that cannot be put into place again. Now that's not the core of the story here. This Roman vase was at a certain point in time suspected to be a work of Renaissance and not of Roman art. And so analysis of these very small shards of the Portland vase could provide an answer there. If we look at the blue and white fragments, you see the high silica, you see the high soda, the high lime, as you would expect in those ranges, and you see this low potash and magnesium values where the red arrows are. These are below 0.5% to 1%, and that is a typical composition of what you would expect for a Roman natron glass, for the natron source of alkali as a flux. And so in terms of date, this Portland vase belongs very well into this natron tradition and in the Roman tradition. Should it have been a Renaissance vessel, then it would have been a plantage glass, possibly mixed with a particular type of ashes that occurs in that period. Another example, rather opposite, is that of enamel. Enamel is a vitreous material, glass, fused to a metal substrate to decorate the metal. And here we have the example of Romanesque enamel made in the Rhineland, Germany. And so this opacified glass are stuck, not glued, but molten onto a copper base. And so the question there is, what is the composition of the glass? Can we find a tradition that links with it? And then you see with the medieval enamel, the first column, and in particular, we're looking at the potash and the magnesia again. We have second line magnesia, 0.5%, fifth line potash, 0.6% in the medieval enamel. Now, this would point to, again, a Roman glass tradition, low potash magnesia. Now, these are 12th century enamels where the vitreous material on the metal should be equal to medieval glass. And so in medieval Europe, we're looking at this high potash wood ash glass. Which you see in the last column, an example of a medieval window glass. This is not the case. And so, is this a fake? Is this wrong? Is the enamel older? In this case, no. These enamels are anachronistic. They are natron glass in a period later than what we would expect. But Theophilus writes in the early 12th century that glass mosaics from pagan buildings, as they are called, basically Roman mosaics, are recycled and used as a sort of secondary resource for enamel work. And so this figures again with the analysis of the glass. In this way, there are many different types of glass technology, mainly based on flux and some based on different silica sources, that you can distinguish over time. And not only time, but also region is variable in some of these chemical groups. And so you get the possibility not only of technological dating, but also of provenance research. Where does the primary material for this glass come from? And as a small sidestep here, and this is the only thing I'll be mentioning about glaze, this is also possible for glazes on ceramic. There are different technological traditions that you will find in a certain time period in a certain geographical region. And in this way, again, this technological dating and provenance work is possible on glazes, because this is basically a glass of vitreous materials, but then stuck on a ceramic base. Now, this provenancing research can be quite interesting. This is an infamous example of glass found on the shipwreck, the Bronze Age shipwreck off the coast of modern-day Turkey, where through the application of analysis of trace elements, you can see not only the glass tradition, but also the origin of the glass that you find on this shipwreck. And so these elements are typical for a certain production, certain time region, and that you can reconstruct from analysis in your archaeological find site. We can go even further with this type of analysis. This is my own work with isotopes, where the question is, during the Roman imperial period, where are glass factories situated? Where is glass effectively made? And so from excavation, the only primary glass making facilities that we know, where you mix the silica and the flux, in this time and age natron flux, and then melt them into glass, the only known factories from excavation are situated in Egypt and in Syro-Palestine, modern day Israel. And so there are suggestions from ancient literature, in this case from Pliny the Elder, that suggest that glass was also made elsewhere, for instance, in the Hispanic Gallic provinces and in certain regions in Italy. And then you try to find a particular marker that you can have in glass found anywhere, because you refer to the primary raw materials, to the mineral mixture, that is what is kept in the chemistry of the glass. You look for a marker that could give you different places of production. With Greco-Roman glass, the case is that most elements, major elements, actually do not distinguish this glass very well. This is all the same glass tradition, natron glass, for a very long time span, from the middle of the first millennium BC until the 8th, 9th century AD. You find this natron glass commonly. It's all the same tradition, type of flux used. And the chemistry of this glass sort of prevents a lot of different glass groups to be recognized, because what you want is a colorless glass that you can blow into shape, that you can mass produce. So there is little variation on this type of major and trace element chemistry between those glass types or regional productions. What we then resort to is to look at the basic characteristics of the silica used. If you use sand, silica sand, quartz-rich sands from different areas around the Roman Empire, say the Sahara versus Egypt versus Northwestern Europe, there is a difference in geological age and composition, and that you can trace again. This is inherited in the glass, and you can analyze in the samples that you find on any site. Now, this is very heavy geochemistry. This requires a lot of time and work, but you can make a distinction in the provenance of glass factories over this Roman Empire by comparing to the basic characteristics of the raw materials. The same thing can be done for this natron type itself. We do have the Egyptian sources that are mentioned many, many times, but the question there is, are there other sources? Is there any other source of this type of flux, this sodium-rich salt, that you could mix with silica sand and then make into glass? And there the tracer that we developed are boron isotopes. Boron is an element that comes into the glass mainly with the salt, in parts also with the silica source. You have a mixed signature, but there you can again find different sources and compare a signature to primary glass, work glass, etc. The drift of this story is that North African, there are several sources of natron in the whole of North Africa, which basically display the same chemical characteristics, which you would expect. They have the same source material, the same age, the same precipitation mechanism, but they are different, for instance, from Greek salts that you find in Lake Picrolimni, and this is very different and doesn't match the signature of the Greco-Roman glass that we find. So there the story or the conclusion would be that this Greek salt is not consistent with being used in Greco-Roman glass production. Now, all this, there is some literature here that is open access on development of those techniques, what the detail of these techniques are. You're free to download that with the databases as well. There is also another StarC lecture online that you can find, I think, on YouTube or through the StarC sources, which explains this isotopic analysis more in detail for the glass. But bottom line is that with the glass that you find on your excavations, you can do quite a bit of chemical work that leads to technological traditions, that leads to technological dating possibly, and provenancing of raw materials, always keeping in mind that the chemical composition of this glass reflects the primary raw materials, the sand, the flux, the colorants. it does not reflect the shape, the typochronology, or the place where it was shaped into its form that you may find as displayed here on this picture. The good thing about this chemistry, typochronology will give you possibly a secondary production place, the hand of the artist that might have formed this type of vessel, or possibly a type area for it. The chemistry will give you the primary raw materials and where the glass was basically made as a new man-made material. Now, you often do not find vessels like this. These will be more rare in your excavations. You do often find vessels like this. The good story there is that even with those little small pieces, you can do quite a bit of chemical work and unravel a history of these types of glass fragments, while you may not have the typological story behind it with these fragments. An interesting case is that of weathering. You see the upper left example of a core-formed vessel, which is basically decolored. It has altered over time. It does not display its original colors, its richness in color palette, as you would expect. But this is an example of chemical surface analysis where you do a scanning of the elements over the surface of this glass shard, typically something you would do with XRF techniques that are entirely non-invasive, non-destructive, and where you would see certain elements in higher or lower contents. And because of this correlation between elements, you can look at technology and you can reconstruct the original colors of these fragments, of these lines, of this patterning on this glass shard. And for instance, lead antimonate and calcium antimonate would give you white and yellow, while the copper antimonate will give you opaque blue. So you can make a chemical looking back at the original state of this glass vessel. In terms of chemical analysis and sample use and sample consumption, while original analysis took up quite a bit of the material that you would excavate, it would take powdering and dissolution, etc. Some of the modern chemical techniques do no longer require such sample consumption. And so I believe you've had or will have an in-detail discussion of what portable XRF can do and how it is possibly different from traditional benchtop XRF or micro XRF. The previous picture is not made by portable XRF. That is done under vacuum conditions with a micro XRF. But portable XRF gives some options there to, in the field, already look at compositions, possibly grouping, but I'm sure Marcos will tell you more about that. But for heavy element analysis, even low contents on small samples, techniques are available now, such as laser ablation, ICP, which only take a pinhead, literally, a couple of tens of micrometers across from a sample, and that can give you a full range of elemental data on your materials. Now, for the isotopic approaches that I use, we still go ultra trace. We still destroy 100, 200 milligrams of glass in powdered form. But these techniques, when your shard, when your glass object fits in the sample chamber of the laser ablation, you can have excellent analyses for a whole range of elements that can give you that technological dating or provenance information. There is work being done on how to further develop this laser ablation work and how to further develop this also into the realm of, for instance, isotopic research, because these ultratrace elements and isotope analysis become more and more important, not to do the technological dating, but to do the provenance work and to do the exchange and trade of glass materials. There are developments in laser ablation that will give you not only non-destructive, non-invasive analysis, but possibly also in situ analysis with laser ablation. There are systems being developed, and some are active, where you bring this type of equipment, which weighs a couple of kilograms, into the field or into a room, and you can ablate away a very small sample that is caught onto a filter, and that filter can then be processed in the laboratory for excellent analysis of trace elements and good analyses of isotopic work. So developments there allow you to reduce sample size and go in the field to sample, which for some instances where work in the field is the only thing that is possible, or even full sample export is impossible, but local techniques cannot give you that information, to give you a minimized sampling that you only basically send the filter to the laboratory for analysis. This one I will skip. You will see or have seen already much on portable XRF techniques. XRF is an excellent technique to see elements, but there are possibilities and limitations to the technique in the field in portable form. You know this is a periodic table of elements. Basically, for each glass technology, each glass tradition, you can link some of these elements to some glass raw materials. And so they will tell you something about the source of that raw material, the mixture. An issue there is possibly recycling and mixing, which is of course a real option in glass research. This type of information can give you quite a bit on what element in what content gives you what type of information. And so a recent thing we published just now in Archaeometry is a review of those elements and isotopes in glass. And I gladly refer you to this paper if you have a question on a certain raw material of glass, or you have an element that you do not understand in an analysis table. This is something to resort to see where can it originate, how did it end up in a glass, and what can it tell me about my glass technology and glass dating. There are still a couple of gaps in this table. The gray elements, some possibly are not useful, and some need some development. And for that, we do need help of other sciences and archaeologists to supply us with the correct materials to browse through this catalog of elements that can undoubtedly tell us more about glass technology and glass provenance exchange trade through time. I think that's about it for me. If there are any questions, I will be very glad to answer them. And hopefully this was somewhat clear for your further work. Thank you.
Thank you very much, Patrick. Let's have questions. We're ahead of time, so that's good. Thilo.
Thank you, Patrick, very much indeed for this very good overview. How far are we with these laser ablation measurements and isotopic ratio determination? Is that, I understand you are working on it and there's promising development. Can you give us a little bit more?
Sure. In the field, there are issues of contamination. So when you take this equipment into a museum or into a field circumstance, you have a very small sample that you catch onto a filter, but the ambient conditions are often quite difficult. And so there are issues for some elements, for very low elements that you do find in the environment, you may have an issue of contamination. So really on excavation analysis might be difficult for anything that is very low content in your glass. In a museum application, it becomes more feasible because there you have more pure conditions to take your sample. In terms of which elements can be analyzed, you have low and higher elements in terms of element analysis, that works well. In terms of isotopes, it depends. There are 3 elements that we would analyze standard in glass, which would be strontium, neodymium, and lead. Strontium and lead are quite easy to analyze, so that works well in laser ablation on filter digestion. Neodymium is so low in glass that it becomes very difficult to even in controlled laboratory conditions to measure neodymium isotopes through laser ablation, leave alone in portable laser equipment. So for neodymium, no successful results so far. For strontium lead, we can apply that laser ablation approach for isotopes.
Marcos appeared.
Hello, Marcos.
Hello, Marcos.
You see, this seamlessly goes to portable XRF and the possibility there.
We have more questions for Patrick from the online audience.
There is a question from Amin Emani. For ICP-MS analysis of little crust pieces, should the surface be cleaned or we can analyze them as bulk? And
yes.
And a second part of the question, I'm wondering what does selenium do in Sassanidine glasses? Those selenium came in association with copper.
Okay, to answer the first question, what we usually do if glass is not cleaned and you apply laser ablation is first fire the laser for a couple of seconds. And that will clean the surface quite thoroughly. You just discard that material that you've evaporated, basically. And then when you see you have a stable signal in the glass, you take your sample, be it in the lab for measurement or on the spot to clean. Of course, you can first clean a full shard or a full object, but in principle it's not necessary because you can ablate a very small spot using the laser, using your analytical equipment basically to first clean the surface and then take your sample for analysis. I'm not quite sure I understood the second question. Is it about the element selenium? SE? Yes?
It says, I am wondering what does selenium do in Sassanian glasses? Those selenium came in association with copper.
Selenium is an element we have difficulty understanding. There's a couple of elements that we see currently, or that we commonly see in a number of glass technologies, and they are usually coming in with one of the raw materials in association with, but they often can have multiple sources, and selenium is one of them. Selenium you would expect with typically ore minerals, typically sulfides, and copper could be one of the sources there, certainly. Why they ended up in the glass is another matter. You might have intentionally colored glass, or it might come in with recycled glass. One of the signatures of recycling is that as you mix glass sources, metals become increased, like lead, like copper, like zinc, because they stick to some of the glass types. They are associated with some colors. When you mix those, you get elevated trace element levels of those elements in glass, while they do not influence the property. So they're higher than usual, but lower than the content needed to influence the property of the glass. And when that happens with elements that are intentionally added, also elements that come with those elements, randomly associated, might become elevated in that type of glass. So for a number of these low content elements that we regularly see, we still do not completely understand where they come from and what they're doing in the glass. Selenium is one of them. But the most logical assumption is indeed it comes along with one of the strong colorants, or it might be an indicator of recycling because it came along with one of the strong colorants.
Another one? Yes, we have another one.
It's from the same person again. I am in a money. Continues, via cleaning, I will put away iridescence. Is that okay?
Yes. We don't analyze iridescence standard. It might become mixed with soil. It might lose elements, enrich certain elements, though you wouldn't expect it, for instance, for metals. It could happen certainly for light elements, which are important in glass classification. And so the iridescence we wouldn't analyze. We would either clean it off or, in the technique, physically clean it or chemically clean it. That's basically what's done with the iridescence. Yeah.
Okay, thank you, Patrick. If we don't have any more questions, we're very sorry that you're not here with us. Thank you very much for your lecture, and we'll see all of you in 15 minutes or 13 minutes. Thank you.
Okay, thank you very much.
Agele. Hello, everybody. We are back. We're sorry for the delay. It wasn't Marcos's fault. He was online well ahead of time. But, well, it's Tuesday the 13th, so we anticipate these kind of things. It's a great pleasure to introduce Professor Marcos Martinón-Torres. He is a Peter Rivers Professor of Archaeological Science at the University of Cambridge. He has published extensively on metals, ceramics, pigments, glass, of case studies around the world. He is part of our promised project. We have welcomed him in Cyprus only once, and we really hope that we're going to welcome him here more times. And from what you're wearing, I think that you would have preferred to be here in Cyprus and not in Britain. Marcos is going to talk to us about advances and limitations of portable XRF analysis in archaeology. And Marcos, the floor is yours.
Thank you very much, and thank you for having me, and apologies for the technical glitches, particularly for me having gate crashed Patrick's presentation earlier. That just shows how keen I am to join you. And of course, I would love to be there in person, but at least I'm happy to join you remotely to share some of the wonders of portable XRF in archaeology. And you've already seen some examples in the various presentations, particularly today, some yesterday. But I thought I would start with a relatively pointless but fun thing that I did yesterday, which was creating an engram for the use of PXRF and WDXRF. As I'm sure you know, this is a graph that shows the frequency with which a term appears in Google Books over time. And this basically shows how over the last decade, the impact of PXRF has been growing exponentially, not just in archaeology, but in materials characterization generally, compared to one of the larger siblings, the WDXRF, which importantly remains more or less stable. So it's not as if it's replaced it completely, but it's revolutionized a lot of things that we couldn't do before, and we can now do in materials characterization. More specifically in archaeology, if you want to get a sense of the impact of PXRF, we can do another, perhaps relatively pointless thing as well, which is check the news. And that's what I did, Googling for news to do with archaeology, including portable XRF. And you see some fantastic headlines, such as King Tut's dagger is out of this world because it was made of meteoritic iron, as demonstrated by PXRF. Neanderthals may have sourced manganese dioxide for fire making. We also see PXRF used for the sourcing and screening non-destructively of the stones of Stonehenge. We have an X-ray gun used to pinpoint the origins of pottery on a shipwreck. And also you have my total favorite, as headlines go, that claims archaeologists today make Indiana Jones look like ancient history. Of course, you know, there's some truth in this, and but if you were to believe and just look at these and other headlines, you might think that there is a solution to all of your problems, that you have an archaeological question and you call your PXRF hero and your problems will be sorted. You won't be surprised if I tell you that things are not quite like this. PXRF is wonderful, and today I'm going to try to illustrate some of those wonders, while at the same time outlining some of the caveats, limitations, or critical issues, at least, that we should be aware of when using PXRF, or indeed areas where we should just not bother at all. I'm sure you know this already, but a PXRF stands for portable XRF, of course, and it's an instrument that looks like a hairdryer or like a barcode reader, and it can be used in a handheld mode, as you can see here on the left, or it can be attached to a stand or a box like you see here, where you can have your samples placed inside the box that's shielded and therefore allows for a more protected, easy, comfortable analytical environment. Either way, the whole kit weighs between 5 to 10 kilos, and so you can relatively easily travel with it and take it to wherever you're going to do your analysis, which is, of course, one of the great advantages of this technique, as we will show later. But before we discuss some or illustrate some of the applications, we need to understand at the very basic level, and this talk is pitched at the very basic level for those with very limited or no familiarity. We need to explain what XRF is. An X-ray fluorescence, when you do it in a handheld device, in essence is the same as when you do it in the larger sibling that has been around for 50 years. Basically, what you're doing is bombarding your sample with X-rays. And as the X-rays hit the atoms in your sample, those atoms get excited. What you're doing actually is causing the ejection of some electrons that are spinning around the atom, around the core of the atom, are ejected off, and therefore other electrons from outer orbitals cascade in to replace them, and in so doing they release some energy in the form of X-ray fluorescence, and then other electron will drop to fill this vacancy and again release X-ray fluorescence. And this energy that these excited atoms are emitting are characteristic of those individual atoms. So this is XRF, or energy dispersive X-ray fluorescence in particular, which is what we're talking about here. And with these handheld devices, we have exactly the same, only that in a smaller piece of kit. So you have a miniaturized X-ray gun here that hits your atoms, and then a detector that will record that X-ray fluorescence, turn it into electric pulses that are then passed on to a mini computer, and off you go. You've got your raw data. It is important to note, whatever, that the raw data that you get in XRF looks like this generally. You don't get a table of chemical compositions as you will get in a paper typically, or you may get it on a screen, but that is post-processed data. The raw data looks something like this. It's a spectrum, it's a single line with various peaks, where we are plotting on the x-axis the energy in kiloelectron volts, and on the y-axis the intensity. Between you and me, and this is a simplification, where on the x-axis we find the peak is telling you which elements are present, and then the height of those peaks correlates more or less with the concentration of those elements, how much of that element there is in there. There's other parameters at play, but I'm not going to go into those. And so in essence, it tells us which elements and in what concentrations. We have a system therefore for elemental analysis. That's what XRF does. And in broad terms, therefore, we can compare it to other techniques of elemental analysis that you will have come across. For example, atomic absorption spectroscopy, neutron activation analysis, some forms of inductively coupled plasma. All of these are different apples, if you like, in that they all do broadly the same, though of course each of those has their own advantages, limitations, and optimum applications, which we can discuss later if you wish. But it is important to emphasize at this stage that there are other techniques that have nothing to do with XRF, and which therefore XRF will never replace. They are origins, if you like. XRD, FTIR, Raman, isotopic analysis, microscopy, all of these techniques provide complementary information that is always different from what you will get from an XRF. The other thing worth emphasizing is that XRF will or not answer archaeological questions. That is your responsibility if you're lucky. It will simply, hopefully, help you get there. So we now have established that XRF identifies chemical elements. So it is appropriate that we look at a periodic table to see which chemical elements we are more likely to identify with portable XRF. And you can see that horizontal line that I have across the third row of this periodic table. Anything above that, or indeed on that line, is challenging, and it will depend on which XRF instrument or setup or analytical conditions you are using. So if we look at this periodic table and we think, for example, to start with archaeological metals, well, the elements that we're interested in, the major elements, are all below that line. So if you're analyzing metals from this perspective, great news for you. If you're interested in organic materials, however, which are mostly carbon with some phosphorus, calcium, etc., this is really not your technique. You would not use XRF to identify lipids in pottery, for example. If you're looking at earthy materials, soil, ceramics, rocks, glass, well, they are somewhere around that line in terms of the major elements. So you may be able to quantify those elements depending on the instrument, but it may be more challenging. That's as far as the major components is concerned. But of course, any of these materials, including the organics, have a range of heavier trace elements that we may be interested in. For example, not the major components in the glass, but the colorant in the glass. And those, or the trace elements in rocks, and those can indeed be recorded generally very well with PXRF instruments. So with this little bit of background that I've tried to provide, we can begin to look at some of the practical applications, illustrating some of the many things that we can do with portable XRF. And one of the most successful areas of application has been in obsidian sourcing. As you know, obsidian is a volcanic glass, and pretty much every lava flow that solidifies so quickly has its own distinctive trace element signature. Obsidian is mostly silica. We're not interested so much in the major element, but we look here at 5 trace elements by Ellery Cramp. He analyzed hundreds of geological samples, and on the basis of just 5 elements, you can see he can discriminate very neatly each of the source regions. So we have now, or even sometimes different sub-areas within a source region. And this means we can now project onto these scatter plot our unknowns, our archaeological samples, and determine their geological source with a great degree of reliability. So this is where XRF is allowing the analysis of hundreds of samples very fast with great success. And this is another example of obsidian, where we are, or they are, the authors, projecting these unknowns, in this case, these couple of obsidian amulets, and you can see how their composition plots very neatly associated to a particular geological source in central Anatolia. So sourcing of obsidian and of other rocks, it's a wonderful area of application. But there are, of course, other areas and other materials that we can analyze. And here we have a different example. These come from gold alloys. So they are alloys of gold, silver, and copper. And we are just comparing 2 different regions. On the left-hand side, we have hundreds of analyses of gold work from prehistoric Northwest Iberia. And what you can see is overall the distribution is towards this side of the triangle, because these are all alloys that are quite rich in gold with variable amounts of silver and relatively little copper. That's why there are no dots in this area of the diagram. And this corresponds with the paler yellow lemon color of this gold. We compare it to gold from the Eastern Cordillera of Colombia, of the Muisca, and you can see that the distribution is totally different because there's a lot more copper and no silver, or less silver. Therefore, the distribution is completely different. Now, we can see these distributions easily because we can analyze hundreds of samples very fast. And so we can see these broad patterns as a starting point to discuss then whether these are technological constraints, cultural preferences, what are the behavioral reasons behind these different distributions. But at least they have these patterns to start with, which, if nothing else, raise subsequent questions that we may then address with further analysis. Similarly, I bring you an example here from pottery, and this is an early study by Frankel and Webb on red polished ware from Bronze Age Cyprus. Since then, Maria Dikomitou has done a great deal more work in this broad area, but I thought I would leave it for her to present her own work. But here you can see nicely how we have 3 archaeological sites and relatively well-defined 3 chemical clusters. Now, this alone, based on hundreds of non-destructive analysis, again, would suggest that for this particular ware, each site had its own supply, probably its own clay sources, and there was relatively little exchange of this particular pottery type between the sites. We can, of course, then try to drill deeper and say, okay, there are a few outliers and overlaps, and maybe we want to study these with additional techniques to try and explain them, etc. But this initial pattern is quite compelling and quite useful. You would hopefully agree with me. There are many more examples. This is another early study on cuneiform tablets. There have been more since, where Yuval Goren and others managed to pretty much replicate the chemical groupings that in the past were only visible through invasive neutron activation analysis. And now you can see some distinct groupings. This is Hattusa, there are others. There's some overlaps, but then again, those existed previously with other techniques. And again, we can make our reference groups and then project onto those our unknown samples and materials. The same applies to glass, and glass is of course a challenging material because there are elements such as sodium that are critical to the characterization of glass, but quite hard to quantify accurately with XRF. But we can focus on other elements, and this is what Laura Adlington and Ian Friesman are doing increasingly in their fascinating studies of medieval stained window glass, where instead of, for example, focusing so much on calcium and potassium, they focus on strontium and rubidium instead, and they don't analyze a small handful of glasses. They analyze every single one of the glasses in stained windows using these attachment that Laura designed, and it's called a windowlizer. And basically, they can identify batches of glass, the panes of glass as they arrived at the cathedral, how they were cut into pieces, fitted together depending on the colors. You can identify later replacements and restorations, very, very thorough life histories of stained windows, which would otherwise be impossible using older, expensive, invasive techniques. And as a final example, something similar to what Thilo was showing earlier in an experimental context, you can also analyze soils. And here we have an actual archaeological site where again you have a grid with those various crosses representing the points that have been analyzed by XRF. Now these guns typically come with a built-in GPS, so this is super straightforward. And what you can then do is overlay this kind of heat map that is showing you where you have the highest concentrations of particular elements, and this will then easily guide your subsequent archaeological excavations of where you're likely to find the furnaces, or in this case, particular areas of metallurgical activity. So this very quickly illustrates some of the great applications that you can see, and you have seen more illustrated in the last couple of days in the various presentations. In each of these cases, you should be asking, well, how do I know my results are correct? This is something I cannot emphasize enough. It is essential that you assess the quality of your data. Only you can do that. And the only way to do this, or at least the best way to do this, is by analyzing materials of known compositions, the so-called calibration standards. Here you have examples of two well-known, well-characterized sets that are used, the one on the left for copper alloys, the one on the right for obsidian. There are other sets for these and other materials, but what's important is that you have a set of samples of compositions that are known, so you can, on the one hand, train the PXRF at recognizing those compositions, and on the other hand, check that the instrument is going well. If you're going to buy an XRF, you should invest in buying some of these as well, or acquiring some other way. Without standards, you can't really tell how well your instrument is doing, and therefore your results are questionable to start with. But let's assume you buy the right XRF, you calibrated it for whichever material it is that you're going to be analyzing. Well, is that it? Is this the end of invasive analysis? Will we no longer see sampling such as these? And these are some real but rather dramatic examples of invasive analysis. So you know, this hole you see through a flint axe is a real hole for chemical analysis. These are all older analysis, but look at this poor bronze axe here, which looks like a cheese. It's been sampled so many times and so invasively, and this is almost being cut in half. Is this therefore the end of invasive analysis? Are all of our problems solved? Well, to some extent, you won't be surprised to hear. And this is where we need to introduce a few other parameters for the analysis by PXRF. PXRF is a surface analytical technique. It only analyzes surfaces to a depth of, it depends on the material and other parameters, but typically from a few microns to very few millimeters at most, typically a lot less, more in the order of a few 100 microns at most. So it's a surface technique, optimized for flat, homogeneous, fine-grained, and infinitely thick samples. So if your archaeological material meets all of these requirements, that's your lucky day. Then you're doing fine. If it doesn't, however, and most archaeological materials do not meet all of these requirements, then you need to make much more critical use of your data, or critical calibrations or critical configurations of your equipment and of your data, so you can produce data that can be used and assessed critically. But what's super important here is that it is your role as the analyst to establish that those requirements are met, because the machine doesn't know if those requirements are met. The machine, crucially, will spit results whether or not those conditions are met. So even if your results are wrong, the machine will deliver results for you. It will give you numbers if you ask the machine to give you numbers. But look, for example, at this cross section through a corroded copper alloy. You can see the object surface here, but the way in which this metal has corroded is such that the various elements have precipitated different layers on the surface, as you can see. So if you analyze these metal from the surface, you're never going to get results that are reliable indicators of the bulk original composition of this metal. This is perhaps also illustrated, or even better, on these graphs that I bring here as an example, where on archaeological bronzes, on the x-axis we have the surface result on the portable XRF for lead and tin, and on the y-axis we have invasive analysis of the healthy metal by SEM-EDS. If there was perfect agreement between both data sets, we would see the dots sitting on this diagonal line. And we can see that far from that. There's clearly something affecting our PXRF results, and therefore we can deem them qualitative at best. So this problem of layering of the surface not quite representing what lies beneath, and depends on the thickness and its density, etc., it is a challenge that adds to our analytical uncertainty, and it affects to corroded copper alloys, but also to gilded metals, to painted ceramics, to rock art, to weather lithics and glass, etc., etc. It is something we need to be critically aware of. And here you have another example, again from Laura Adlington, where you can see again for glass given versus portable XRF analysis, and you can see the correspondence for this relatively light element, potassium, is not ideal, because most likely because the surfaces are corroded. So what do we do in these cases? Should we stop doing analysis? Not necessarily. We just have to make critical decisions, either in how we're going to handle the material or how we're going to handle the data, or both. One of the things we can do with metals, and as Patrick was just discussing with glass and other materials, is remove the corroded surface, so we can identify an area that's cleaner and where we can make, more reliable analysis, as you can see there. How big that area, depending on your instrument and your conditions of analysis. This is, for example, what Andreas Haralambos has done here on these early Iron Age copper objects from Cyprus. And this has allowed him to obtain reasonably reliable data that shows that there are two groups of compositions with two modes, one with higher tin bronze corresponding with these bowls, indicating that there's a fresh supply of tin or a fresh supply of bronzes in the period, and other archaeological inferences of interest that, of course, I don't have the time to discuss now. But this was possible because some element of cleaning the patina took place. We took a broadly similar approach with our study of the bronze arrowheads from the Terracotta Army. There are thousands, literally, of these bronze arrowheads. We couldn't clean all of them, but we wanted to clean some to assess the reliability of our data. These arrowheads appear in groups of 100, and we wanted to see if each of these groups was chemically consistent, if all of the arrows in one bundle might derive from the same crucible load. So in one pilot test, we compared the composition of clean surfaces with dirty ones. And hopefully you can see that if the samples are clean, the chemical cluster is tighter. If they are dirty, we get a lot more noise, typically increased tin and lead on the surface corrosion. Bearing this in mind, we can proceed and analyze hundreds of arrowheads and say, okay, our pattern is quite noisy. There are outliers, our groups are quite scattered, but overall, in combination with this, now we look at that, and we can argue that yes, the arrows that appear together, colored in the same color, yellow, red, gray, blue, etc., tend to have broadly similar chemical compositions. Now, this is something that some analytical chemists would say is awful. This is bad analytical chemistry because we have a huge sampling uncertainty and analytical uncertainty. They are right, strictly speaking, but of course, it's one of those cases where we may, as archaeologists, we know we often have to compromise in terms of artifact integrity. And I would argue that this allows us to make archaeological inferences that otherwise would be impossible. But we have to be critical in the use of our data. We have to be aware of how far we can go with our data interpretation. We have to know to what extent we can trust the numbers that we are using. Something similar is what's happening in this study of glazed wares, these early porcelains or Qingbai from China, because we're analyzing glazed ceramics through the glaze. And so you get, in this particular case, the glaze is about 0.5 millimeter in thickness. So most of the X-ray fluorescence is coming from the glaze, but inevitably you get some noise from beneath the glaze. However, with these totally non-destructive approach, they managed to, as you can see, looking at reference samples from kiln sites in China, they identify, relatively well-defined clusters onto which they can then project the unknown samples from the shipwreck. And yes, arguably, you can say there is some noise and uncertainty, but overall, what I would argue is that this is a very conclusive study that has been done totally non-invasively. In other cases, you may want to go completely qualitative, and still it is archaeologically interesting. So here, we are not looking at actual element concentrations. All we are saying is for the later part of the Middle Bronze Age, there is a much higher frequency of alloys that contain tin. So compare these bars on the right to the ones on the left here. So that alone is significant and meaningful, and something that might then lead to subsequent analysis with other techniques, but at least as an initial screening, it is very useful for some of our archaeological purposes. You have seen previously analysis on the surface of used crucibles, for example. So we analyze these crucibles, and we see in the spectrum qualitatively that there are peaks for copper, tin, zinc, lead. What can we say? Well, we can confirm something that in this case we knew already, that some degree of copper alloy processing is taking place. Maybe good enough, but we certainly have to acknowledge that we would need other techniques, most likely invasive, to tell whether they are really just melting bronzes or smelting or recycling or any other more specific technical parameters that we might want to investigate. But sometimes qualitative analysis are good enough, and of course that will depend on the question. On this example here, we're seeing, not that I've been doing them myself, what Kelly Domoni is doing is qualitative surface analysis of decorative porcelains, and in particular focusing here on the green pigments. So the spectrum on the right is overlaying two analyses, one of copper green, green pigment being copper carbonate, the other one on chromium green, which is rich in chromium and iron, cobalt, and zinc. So the qualitative identification of one or the other is enough to say, okay, if we have chromium, it's post-19th century. That may be good enough, at least for some initial screening. Other cases where qualitative may be enough is, for example, in the identification of toxic pesticides in textiles. I have said earlier that you can't really identify organic materials through XRF, but what you can certainly do is identify heavy elements that are deposited on those organic materials. And this is the case. Many collections, old collections of textiles and other organic materials in museums were treated in the past with pesticides that contain arsenic, lead, mercury. And so in modern surveys, you can quickly scan those. And if you find just a big peak for lead, well, you know that you should deal with, you should treat that with caution. You're alerted to the presence of a toxic element in your material. So this brings me to one of my last slides, just to highlight another couple of challenges in PXRF or EDXRF analysis generally. One is, of course, the idea of spectral overlaps. When you have too many or a range of elements in the same sample, you can have something as a spectral overlap, such as you have here. Can you really tell whether there is arsenic in this sample? Well, the peaks for arsenic should be one here, they're the blue lines, and another here, but they overlap with peaks for lead, which are here, and in this case for mercury. And so these peak overlaps become increasingly difficult to resolve, and in some cases, you may just have to move to other techniques. For example, WDXRF, one of the bigger siblings of PXRF, that will resolve this question better than you would with a handheld. The spectrum also illustrates something that you can see in any XRF spectrum, which is the kind of background noise that we see here. And this is what establishes, if you like, the detection limits of the instrument. This background noise depends on a variety of parameters. We can try to optimize it, but it's always there. And it means that if your peaks are so small that they are beneath that background noise, you do not see them. So there's a threshold below which you cannot really tell whether one element is there or isn't there at all. So this has been a rather quick, I acknowledge, overview of various case studies, potentials, and problems. And I hope we can end on a positive note, highlighting some of the many things that go with the portable XRF. The portable XRF is fast, is versatile in that it can be applied to lots of different materials, and you can take it anywhere, even to the field, because it's rugged and it can, it's quite hard wearing. And because of that, it is allowing us to take analysis to places where we weren't able of doing them before. And one of the things that I like the most is that it allows for adaptive or sequential sampling. You can analyze hundreds of samples, see broad patterns, and sometimes that's good enough. But if not, you can then do the subsequent analysis or sampling with other techniques, but on a much firmer ground, with a better understanding of what your material looks like. So it's almost as if you have an additional pair of eyes, an additional variable in helping you sort through, select, and characterize your assemblages. XRF is, of course, non-invasive, though with the caveat that if you're completely non-invasive, your results may not be quite as reliable as you would like. It is affordable, which is a relative term, of course, but it is more affordable than most analytical techniques. And because of this, another thing that is among my favorite, XRF is actually making archaeological science accessible to individuals, to departments, to teams that otherwise had no means of accessing science. This means that we are taking the science away from those ivory laboratories in well-resourced universities and making it accessible to a wider range of studies and people and students. Students are people as well, of course. But there are notes of caution that we should be aware of, and I'll finish here, that perhaps curators and colleagues and users generally should be aware of. One is that invasive sampling may be required, contrary to some expectations, that you really need to understand what XRF does so you don't make a fool of yourself. You need to understand the foundations. You need to understand what it can or cannot do in a particular situation. It is not the solution to all your problems. It's only a solution to some of them, perhaps. Importantly, each material requires its own setup in terms of calibration standards, accelerating voltage, filters, etc. So an instrument that's been very good for obsidian may be awful for copper alloys and vice versa. Another very important point is that the instrument will spit numbers even if they are wrong. The instrument doesn't know. That's why you need to know if those results are right or wrong, or the extent to which there is an uncertainty. It doesn't answer archaeological questions. That thankfully remains for us to do, so that we will not be completely replaced by machines. It doesn't really make you look cool. Thankfully, gone are the days of somebody turning up with their cool X-ray gun at an excavation and being the coolest guy at school. And finally, perhaps in terms of the challenges to highlight, what I also highlighted as an advantage is the accessibility. PXRF is now available to almost anyone, and that is wonderful. But with that comes risks and responsibilities. We've all seen studies out there that shouldn't have been published, perhaps shouldn't have taken place at all, and they are taking place because a PXRF is now potentially in anybody's hands. And that is why, like with any new technique, it is essential that we work with each other, that we educate ourselves so that we can become critical users and consumers of this technique, which is otherwise fantastic. And this is what I had for you today. Thank you very much for your attention.
Thank you, Marcos. And we have questions.
There are two online questions. The first one is from Amin Emami. Question: how can we judge that the results on ceramics powder have been done well or not well enough, because they are mainly contained from silica, aluminium, or calcium?
That's a very good question. And as I was saying, ceramics, like soils, the major elements can be quite challenging to measure. Now, there are instruments keep getting better and better, and some of them have a helium flux that allows you to detect light elements in lower concentrations and more accurately. The first thing I would say is, of course, reference materials. You need to analyze materials for which you know the composition, and so you can basically test the performance of your instrument. So you analyze the standard without telling the instrument, or more ideally, without telling the instrument what the composition is. You ask the instrument to determine that composition, and then you can see how good or bad the instrument or your particular setup is for a particular element or concentration range. The other thing that you will see people doing mostly with ceramics is that they don't focus so much on the major elements, but rather on the mid-set trace elements that are better for discrimination of pottery sources or pottery recipes, and those can work very well. With XRF, and I'll try to finish, we have the additional challenge that, with XRF of ceramics, that ceramics can be very coarse in their mineralogy. They can have, the finer your ceramic, theoretically, the closer to optimum the matrix for XRF analysis. If you have a lot of large minerals and your ceramic is heterogeneous, that will again invariably add noise to your results, which is something that there are ways of assessing and quantifying. There is a paper by Ellery Fram in JAS in recent years assessing, the impact of rather coarse-grained ceramics on XRF analysis. So ultimately, it can be done, but you have to make critical use of your instrument, and you have to demonstrate the reliability of your results, so you know how far you can go with them.
Do we have another one? Yes, please.
There is one more from Emami. Arsenic is volatile. Is it suitable enough for analyzing corroded arsenic bronzes where arsenic was contaminated on the near surface area?
So I'm not sure I understood the question. Arsenic is volatile, and therefore whether we can analyze it in ancient copper alloys specifically. Is the question along those lines? So arsenic, well, I'll try to, if I understood the question correctly, if not, ask me again. So arsenic is indeed volatile. So every time you remelt arsenical copper, you will burn off some of your arsenic, but however much arsenic is left in your copper alloy, you should be able to detect and quantify through portable XRF. Now, if your arsenical bronze is corroded, you are quite likely to have an enrichment of arsenic-rich corrosion products on the surface. Arsenic itself, even before it corrodes, is prone to arsenic segregation or inverse segregation, whereby you have more arsenic on the surface than you have in the bulk. So it is one of those elements that is going to be challenging to quantify reliably through XRF. And that's where it may be better to simply determine it qualitatively, how, whether or not you have arsenic or separate low arsenic from high arsenic. So I'm not saying in these cases you shouldn't analyze it. You should simply make, once again, critical use or critical assessment of the quality of your data.
Άλλες δύο ή ο ίδιος? Ναι, έλα.
There are still two more questions. So the first one is, do PXRF instruments have imaging so that the area analyzed can be located to target more homogeneous areas or inlays, etc.?
Yes, most of the newer PXRF instruments have a little camera with a circle in the middle, so you can see not a very high quality but good enough image of whichever area of the sample you're analyzing, and then a circle or a laser pointer in the middle saying this is the spot that you're going to analyze. So this is useful, for example, if you're analyzing a multi-component thing, say a ceramic that has various lines painted in different colors, and you want to analyze each of the lines. So yes, you can select areas that you think are optimum, or if you're analyzing a core ceramic and you want to pinpoint the matrix and avoid larger inclusions. So yes, this is possible, though I would just give you a bit of warning that it is important that you check that the collimator is always aligned with the laser, because that is not always necessarily the case. It's something that a lot of people take for granted, and when you go and check, and there are ways of checking, when you travel with these instruments, sometimes they can get misaligned and the pointer is pointing at one point and your analytical spot is 2 millimeters to the right and analyzing something different. But yes, it is possible. That's the short answer, I suppose.
The last question from Manuel Peters. When using PXRF data for PCA, do you set the cutoff point for components yourself, so just including the main elements, or do you let MATLAB or R decide statistically which components to exclude? And a clarification on that. Do you remove, for example, non-metallic variables before doing PCA, or do you input the full raw data set with all elements in the software?
No, I'm very glad you asked me this question, and I'll try to address it briefly. No, you cannot just let SPSS or MATLAB or R to do the job for you. That's where you have to be a critical user. So you produce your XRF dataset, and people are sometimes tempted to just run it through the multivariate statistics, see which groups you get, and off you go. Before you do that, you need to first establish which elements of your spreadsheet are reliable, which you establish through comparisons with reference materials. Having established which elements are reliable in terms of your analytical uncertainty, you then need to establish which elements are informative for what you're trying to do. So, for example, elements that are prone to post-depositional contamination, say phosphorus or sodium in ceramics, you would not include if what you're trying to do is provenance those ceramics, because you know those are not reliable through provenance. They may be reliable if what you're trying to do is classify your ceramics based on post-depositional alteration. So again, the selection of elements should be decided by the question. If you're analyzing data for glass, it may depend on whether, as Patrick was saying, whether you're trying to identify different sources of sand or different types of colorants. Then the elements of your data set that you're selecting are different. So it is really important that before you use any form of multivariate statistics, that you look at your numbers, that you have an understanding of what each element is informative of, what the question is that you're trying to do, how reliable each of those elements are, and generally just try to eyeball things. Start with individual bivariate scatter plots. Familiarize yourself with the numbers so you get to understand what's normal and what isn't, rather than just hitting 3 clicks and expecting to generate these beautiful graphs that may be totally meaningless and in some cases just illustrate the lack of critical understanding. And that's really what's damaging sometimes PX reviews. People use the gun, crank a poll to get a PCA or hierarchical cluster analysis, and off you go. And you need to understand a bit better what you're doing if you want to be a critical consumer or producer of archaeological science.
Thank you very much, Marcos. Unfortunately, we don't have more time for questions. Thank you very much for this wonderful lecture, and we hope that we're going to see you soon in Cyprus. Or soonish, so. Anyway. Thank you. Bye-bye. Bye. Okay, and this brings us to the last lecture of the, not only of the day, but of the workshop. And we have to welcome Dr. Artemios Oikonomou, our very own Artemios, that he works with us at StarC, and we're very, very happy for that. He's going to talk. He's not going to talk about glass that he usually talks about, but he's going to talk about first aid for artifacts and sites, the role of archaeological and conservation science, and I'm sure that he's going to put a twist in the talk that we haven't heard before. Artemis?
First of all, thank you, Evie, for this kind introduction, and thank all of you that are still here and all the people who are online. And as Evie said, I will be talking for the next few minutes, hopefully, about first aid for artifacts and sites and the role of archaeological and conservation science. This is the outline of my presentation. At the beginning, I will start with a few definitions about cultural heritage and the need to preserve it. About conservation and archaeological science, highlighting the common grounds of the two disciplines. And then I will continue with some practical considerations and the first measures we should take in situ to preserve more effectively and efficiently cultural heritage. So according to ICOMOS, I'm sure most of you are familiar with ICOMOS. It stands for the International Council of Monuments and Sites. Cultural heritage is an expression of the ways of living developed by the community and passed on from generation to generation, including customs, practices, places, objects, artistic expressions, and values. Cultural heritage is often expressed, let's say, and can be distinguished in two main categories, the intouchable and the touchable cultural heritage. In touchable cultural heritage, we may include buildings, monuments, books, works of art, and artifacts, and let's say in general, what we can sense and touch. While on the other hand, the intangible cultural heritage is a more abstract concept, and it includes folklore, traditions, language, and knowledge. Apart from this, we should also take into consideration natural heritage, with which we can define culturally significant landscapes and biodiversity. So why is it important to preserve cultural heritage? We can say that there are a lot of reasons, but just to name the three most important ones is that cultural heritage, it has an educational, let's say, concept. We educate ourselves by studying it, and we pass the knowledge to further generations. And this has also a social impact through the knowledge, because we become better people, and so we make better societies. This is a very general thing. And of course, we have the economical factor, and we can say that cultural heritage is associated, let's say, with the GDP of countries because it is also connected to the tourism. And for example, a lot of countries in EU and beyond have museum sites that people visit, and so they gain a lot of benefits. Among the various disciplines which contribute to the preservation of cultural heritage, conservation science has the most crucial role. So conservation science is the interdisciplinary study of the conservation of art, architecture, and cultural heritage in general through the use of scientific inquiry. And actually, this scientific inquiry is the connected key between conservation science and the archaeological science, as we will see in the next slide. There are three broad categories that the conservation scientists work. And we can say that, first of all, it's the understanding of the materials and techniques used by the artist. This is a very important task since it can give information regarding the conservation treatment to be followed by the field or the lab conservators. The second one is the study of the causes of deterioration, and also a very important task. In other words, to identify and to study in depth the mechanisms that cause the deterioration of an artifact or a site. Finally, the third domain is to discover or to improve existing methods, techniques, or even materials which are used for the conservation of cultural heritage. Therefore, it is obvious now that conservation science is driven by this scientific inquiry and also includes many disciplines like chemistry, material engineering, and many more. And it can be, let's say, an interdisciplinary discipline. At the same page, archaeological science, by definition, consists of the application of scientific techniques to the analysis of cultural heritage. Therefore, we can see that between the two disciplines, we have two main common factors. First of all, cultural heritage, of course, and then the scientific approach. In general, we can say that scientists from the natural sciences assist to the scientific analysis of cultural heritage, and as with conservation science, in archaeological science, we have many disciplines such as chemistry, physics, geology, and many more. Archaeological science, in archaeological science, there are a few subfields, which include dating, material characterization, archaeobotany, human remains, digital archaeology, and many more. So, therefore, we can see that both disciplines have common grounds. First of all, the main objective, the general issue, is the study of cultural heritage. Both use, let's say, the same tools, that is the combination of various disciplines, as I said earlier, and they both have a scientific approach in their studies using many disciplines and state-of-the-art methods and equipment. And of course, they both need as a background all the historical, archaeological, and art historical information and data. However, the focus of each discipline is a bit different. For example, conservation science cares about material characterization and the corrosion mechanisms in order to understand the current state of the material and to identify its decay and the corrosion mechanisms. And of course, to suggest appropriate strategies to conserve the materials. On the other hand, archaeological science, generally speaking, aims to identify where when and how a material was made, which can be further extended to identify socioeconomic and trade activities, and in general, let's say, to reconstruct past civilizations. And how both disciplines are associated with first aid measures. Both disciplines are highly connected, to my opinion, with first aid measures. The conservation scientist, apart from trying to improve and invent new methods for conservation, tries also to ensure the survival of the material. And at the same page, the archaeological scientists need the survival of the material in order to have something to further analyze in the lab and to solve the major archaeological questions. Therefore, this parallelism, which is borrowed from the health sector, is a very to-the-point expression, and actually it is what it says, that we need first aid measures to try to preserve the materials which are at risk or in need of further treatments. In the next few slides, I will be talking about how we can plan a conservation treatment, what are the main factors that affect the stability of an artifact or a site, and a few examples of first aid measures that we do in situ. Regarding the conservation planning, and as part of the first aid measures, there are a few steps we need to follow prior to the thorough scientific analysis and before, let's say, the lab treatment. First of all, we need a detailed documentation, if possible, of the object, the heritage site or the artwork, enriched with all the available historic archaeological data. And secondly, we need to diagnose the current state, preferably in a non-invasive way. Finally, we need to be able to assess the current state and potential risk of future deterioration of the materials under study. So, starting the documentation of the artifacts and sites, it is very important to understand and being able to distinguish the materials found in the field. The condition of all materials is actually a result of their interaction with the surrounding environment, and usually different materials react differently to the same environment. So it is very crucial to be able to distinguish the materials found in the field, and this is a very general diagram which distinguishes the materials in the two main categories, the inorganic and the organic materials, which are further distinguished in metals and non-metals, and the non-metals can be distinguished in the modified materials and the natural ones, while on the other hand, the organic materials can be distinguished in animal and human remains, in plant remains, and synthetic materials. So the most important thing that we have to take into consideration when we are about to apply the first aid measures is the various environmental factors which can cause or influence significantly the deterioration of the artifacts. It is true that all material remains interact with their environment, whether their environment is the burial environment or the environment after the excavation or even the storage environment. Environment actually is the key factor which can cause immediate or long-term changes and the deterioration of the materials. Environment generally can be expressed with various factors, which in other words called as agents of deterioration. The degree of these agents of deterioration affects the materials. It depends on the area. For example, when we are in an urban area in Central Europe, the main agent that we should take into consideration is pollution, while when we are in a site which is by the sea in, let's say, in Eastern Mediterranean, like in Cyprus, we have to take into consideration other factors like, for example, soluble or insoluble salts. So, I have chosen few of these factors that affect, of these environmental factors that affect the materials, and which apply mostly to the environment of Cyprus, let's say. First of all is the water and relative humidity. Both can indirectly affect the artifacts and sites, in the sense that they can fill pores or move between cracks and holes, and can carry with them a lot of elements, unwanted elements, like, for example, chemical elements, which can directly affect the materials. Cyprus, since it's surrounded by the sea, can reach up to 75% or 80% of relative humidity annually, and is never lower than 55 to 60%, which is actually the upper limit, the upper acceptable limit for relative humidity. Water, in every form, can affect more or less all materials, but the inorganic non-metals are the least affected. Secondly, temperature is one factor that in most cases increases the rate of most chemical reactions. The sun can heat up the remains and material and cause them to dry out quickly, and this might affect the materials. Temperature can affect materials directly, and in combination with relative high humidity, it can cause severe problems to the remains. Average temperatures in Cyprus, as you know, range at around 15 to 45 degrees, and depending on the time of the day and the year, and this might be very bad for the remains. Salts can be very destructive for the materials. In Cyprus, salt can affect sites which are in close proximity to the sea. For example, Hala Sultan Tekke, which actually is next to a salt lake, or Amathus, or the archaeological park in Paphos. And salt is deposited on materials with the aid of water, and when it evaporates, can leave behind incrustations on the materials, which can be very harmful. Salt affects most of the materials and can create corrosion in stones, and also can do physical damage in non-metals and organics. In addition, oxygen can be very harmful, since it's one of the essential ingredients which helps chemical deterioration, reactions, and of course biological growth. Especially it affects metals and organic materials directly, while it can affect all other materials indirectly by the biological growth, which is aided by the oxygen. It has to be taken very seriously into consideration when we unearth objects, either from soil or underwater. These objects are buried in environments of low oxygen, and when they come to light, can be destabilized and start deteriorating very fast. Therefore, as we will see later, immediate action should take place in situ to avoid any loss of valuable information, even the material itself. There are a few more factors, environmental factors, that affect the deterioration of materials, but I want to elaborate more. This can be light, and especially UV radiation, which affects directly the organic materials, winds which move water, sand, various pollutants and cause erosion, biological growth, as I said earlier, acids and alkalis, which can be carried by groundwater and exist in the soils. And last but not least, human action by altering the surrounding environment and doing any agricultural activities and so on. Okay, so the period after excavation is very crucial, since the remains will try to reach equilibrium with the new environment. During this period, most of the deterioration occurs. Needless to say that in most occasions, in most cases, more than one of these factors affect cultural heritage elements, making the work of conservator and conservator scientists more complicated, and the need of first aid measures immediate and more imperative. In order to deal all these circumstances in the field, it is a good practice to do a field checklist in order to be as well organized as possible, because this is a very crucial and essential step. We should act fast and effective, and so as to stop and detain as much the deterioration as possible. And new features and conditions changed in exposed materials, and constantly we have to identify the at-risk materials, assessing their condition and their stability. These are some of the key factors we should include and consider in the checklist so as to be as prepared as possible in the field. For example, at-risk materials, artifacts, or in-situ remains must be prioritized and made stable by temporary measures or by processing on-site. If this is not possible, then they should be stored and moved with all the appropriate precautions at a more stable and organized lab environment to be further treated. In general, there should be good organization of the actions which will take place in situ, because time is pressing, is very valuable, and also we may face unpredicted circumstances, and so we need to be more effective. So why sorting the materials in an excavation is important? Because correct sorting is critical to reduce the risk of damage of the artifacts. Sorting can streamline processing and can improve efficiency, and artifacts are generally sorted by material type and condition when excavated. The first thing to do when artifacts are removed from the field at the first level is to sort them into material types. We have the basic two categories, the inorganic and organic materials. Sometimes we may face some composite materials, for example, a metal dagger having a wooden handle, or we can even have materials that we cannot identify. We cannot be sure what kind of materials they are. In this stage, we can use the aid of archaeological science, having a portable equipment, for example, and to be able to identify the material in order to proceed with the further sorting according to the main categories that exist. So at a minimum, artifacts should be sorted to level 2, except metals, which should be sorted by type at level 3, because we need to prevent any accelerated corrosion between different types of metal. It is generally accepted and ideal to sort materials and store the artifacts on the day of excavation to avoid any kind of deterioration. So the things that I want to note now is that sorting and distinguish the materials in situ is a critical phase, and this is because vital information can be easily lost during this process. we have to be sure that all contextual information is retained with archival and permanent labeling, for example, plastic labels and water-resistant markers and so on. And we should label and identify any suspected hazardous materials or materials from contaminated deposits, because this actually will help us for the further treatment and the further study of materials when we are in a lab environment. Finally, and possibly most important, we have to be sure that no information is lost for further analysis. Both days, in the first day and today, people who presented made it clear that we should be careful with the materials in the excavations because there is a lot of information hidden in places that we cannot see. So we have to be as organized as possible, and we have a critical thinking and planning to save samples for further analysis and for further, let's say, archaeometrical investigations. After sorting the materials as discussed previously, it is now the time to apply some immediate actions so as on the materials so as to slow down any deterioration effects. These, I believe, to my opinion, are the most common problems we face in the field, and we have to act immediately when possible. In particular, when we notice salts, that is white crust deposits forming at the surface of the material, we need to prevent further drying of the remains by either reducing the exposure to direct wind or to sunlight. And in some cases, we should also consider temporary burial or covering the elements with a tarp or other cover. This is mainly applied to building materials and building elements. When during the excavation we expose fragile remains of an artifact, then we should stop, if possible, the excavation process because it may further destabilize the object. Depending on the situation, we should consider immediate reburial of remains that are particularly fragile, or as it happens in most of the cases, remove the artifact along with some of the surrounding burial matrix. In this case, the burial matrix acts as a consolidator and prevents further collapsing of the material, and the object then is transferred safely in the lab environment for further treatment. Of course, we can provide additional support during excavation and consult, if possible, a conservator, or if there is any conservator there in the site, to give him or her the most possible information to treat the object. When structural stability is at risk, especially when we are talking about walls which are slabbing or collapsing, then we should stabilize the feature as soon as possible using, for example, sandbags or most commonly temporary wooden or metal supports. And we should avoid further excavation below the bottom of the walls because this might result to total collapsing. At this stage, sometimes we can do some grouting and pre-stabilize the walls, but this should be probably should be done from a conservator because we need to ensure that the material we use to stabilize the wall should be compatible with the wall. Finally, one of the most common problems in the field is biological growth, especially on walls and building elements. Usually, especially during spring period, there is significant growth of plants. We should avoid pulling out plants out of the feature because this might destroy the feature. And we can even consider applying herbicides and biocides, but directly to the plants. But this should be done with care because this might affect the element itself. So a very important factor in choosing the best, let's say, or the available strategy for the first aid measures, beyond, of course, those mentioned above, is cost. Many times, the cost of conservation materials is too high, and the availability of these materials is difficult on site. So working in the field is an ongoing process to rescue the finds and with particular resources. So the working groups should be creative and invent new methods to apply the first aid measures. For example, when we use soft materials to avoid shocks, when we transfer objects from the site to the museum or the storage room, we usually, preferably, should use polyethylene foam. But as you can see, it's a very expensive material and difficult to find on site. But styrofoam is an equally effective material which can be used and find easily in every hardware store, let's say, and actually is very cheap. So to summarize, first aid measures are necessary for the preservation of cultural heritage, and it's very important to expand the life of artifacts and sites. Both disciplines, conservation science and archaeological science, contribute significantly to fulfill the main objective, that is the preservation and the study of cultural heritage. Both act complementary to each other, and both have the same subject of research, which is cultural heritage, artifacts and sites, and of course use the same tools, such as an array of analytical techniques and various disciplines, giving them, let's say, multidisciplinary character. They have, though different aims, different, let's say, end product, which for the case of conservation science is the study of materiality, its preservation state, and the development of new conservation methods, while for the archaeological science is the technology, provenance, and dating of the material. However, both aims are highly connected because both disciplines share same information to fulfill their goals. And to close this presentation, I would like to say that here in Starcy, we are doing a lot of archaeological science, from archaeological materials to archaeobotany, and from human and animal remains to digital archaeology. So we are more than happy to help and aid in every conservation and archaeological project here in Cyprus and beyond, of course. Thank you for your attention.
Bravo, Artemi. Thank you very much for that. Yes. Questions? Effie.
Thank you, Artemia. So, a general question and comment at the same time. You mentioned very reasonably how important the sorting process is. However, we have seen here the past couple of days how incredibly difficult it is to identify materials, even at a very basic level. So Evie showed us what charred seeds look like, which is nothing like actual seeds. I showed some baby bones. Thilo showed some slag, which didn't look anything like metal or metal derivative. So who is doing the sorting in the end?
First of all, you, with the experience of the field and the excavations, should do the sorting and try to distinguish the main groups of the material. The first level, as I saw in my slide, inorganic and organic. And then, if there are any collaborators, specialists who you can invite to come and study the material, then they will do the further sorting of the samples.
Can I ask now a follow-up question? In your experience and knowledge, is there a guide out there helping archaeologists who are not specialists in this type of basic sorting?
Yeah, yes, there is.
There are. Okay.
It's one of the second reference that I have on the PowerPoint. So it has a very detailed, let's say, procedure, how to sort materials and how to plan the conservation, let's say, treatment, in case you don't have any conservator in the field.
Which most of the times we don't have conservators, unfortunately, in the field. Do you have any questions? I just want to make a comment to follow up for what you said about the sorting. Again, I'm going to talk about keros. I'm sorry, people. During sorting, after flotation, we found something that, because my OEP is very bad, so Carly Henkel saw it to me and said, "What do you think it is?" I said, "Well, it looks like a stone. I don't know what it is." And because we had a portable XRF on site, we got the person who was handling it and said, "What is it?" And it was actually a rotted silver. It was like that very ugly mass that you couldn't understand what it was. And then when they zapped it, it was silver. And of course, this is a game changer because we have silver on a site that we didn't know that we had before. And if it was me, I would possibly say, "Oh, that's a stone. We don't like it." By the way, possibly not. But I'm just saying how this sorting works. Anything else? Okay, so we would like to conclude this two-day workshop. Thilo, do you want to say something? Okay, hold on, I'll finish and you can say later. We would like to thank all the people involved, all the people that they gave wonderful lectures, all of you that came here, the Department of Antiquities and our collaboration, and we hope that we're going to do more things in the future, and our online audiences. We're going to actually organize more workshops under promise, so I will keep you posted. And Thilo has to say a few words. Thank you very much.
Yes, thank you, Evie. I just wanted to say thank you to you as well, and all the other people at Star C who have actually managed this event, and to Angelos for all the good technical support, rescuing us when some provincial universities linking in had difficulties and such like. So, no, thank you to a lot of people who made this possible, and thanks to all the audience, both in person and online, for all your patience.
Let's have a picture.
Oh, we don't have our masks on, sorry.
Oh, there then.
We are, yes,
there.
2 meters distance.
2 meters, yes.
Yes. We don't want to spread it.
No, we don't.
We want to spread the knowledge, not the virus.
Yes.
Be good. Thanks, everybody.